I'll start the live stream.
Oh, sure, yeah. All right, yeah, looks like we're live on Facebook. Welcome everyone to MLMC Day 2. We'll give it a few minutes for everyone to arrive. And just while we're waiting to get started, I just want to reiterate our gratitude to the community out there and everyone's response to us organizing this virtual meeting this year. We had a really terrific response. We had a record number of abstract submissions. We had almost 50 reviewers volunteered to review abstracts. So every single abstract got reviewed by 5 or 6 different reviewers. So it was a real kind of big effort from many people that went into organizing the lineup of this meeting. So thanks very much to everyone who submitted or helped out with the review process. Let's just give it a couple more minutes. We have still people joining us. Also,
I also want to just maybe just jump on it and say to everyone, in case somehow you weren't able to make yesterday's session or weren't able to see every talk or would like to see something again, God forbid, there is a recording of yesterday's session available on the MLMC website that everyone can look at.
Yeah. And I guess just one more other thing to mention is we do have in addition to this Zoom webinar, we have a live stream on Facebook. If for any reason people have problems connecting via Zoom, if we hit our capacity limit, which we were reasonably clear of yesterday, but you never know. The live stream on Facebook will be available no matter what. And that you can also find on the meeting homepage.
And we do have a Q&A dialogue box during and after the talks. So to help keep the questions separate, please, when you put in your question, just put the first name of the speaker, first or last name of the speaker at the beginning of the question, so it's easier to keep track of them and the responses.
Okay, well, it's 11:04, so I'll go ahead and get us started. So our first speaker today is James Finlay. So James was a postdoc in Amy Bastian's lab when I first got to know him. We were both postdocs there. And he worked on energetics of locomotion there and how that changes and influences adaptation. Prior to that, he did his PhD with Eric Perot at Northwestern University. So James is now an associate professor at USC, and his lab tries to understand why it is that we walk the way that we do. And his lab there brings together the variety of perspectives from engineering, physiology, and neuroscience to try and understand this question of why we walk the way we do. And I've always appreciated that James is particularly thoughtful about the idea of optimization. So for many of us, optimization is just kind of the integral of u squared dt, but James is always kind of has a lot of insight and thoughtfulness about what exactly is it that we're optimizing, if we're optimizing anything at all. So I think we're going to hear something a little bit along those lines today from James. So I'll hand over to you, James. Looking forward to hearing.
All right. Well, thank you, Adrian, for the introduction. This is morning breakfast time here on the West Coast, so you will likely hear children talking in the background over the next few minutes. So I'm going to go ahead and share my screen. Let's see if I can get this to work. Okay, share my screen. And okay. All right, can you all see my slides?
Yep.
Okay, excellent. So I'll go ahead and get started here. So first of all, thank you to the organizers for the opportunity to share some of the recent work we've been doing in the lab here at MLMC. I want to start by just acknowledging some of the current former students, postdocs in the lab and close collaborators who really have led a lot of this work. So I wanted to get that out of the way up front. So I really appreciate their contributions. And really, I'm going to talk today about two concepts that I've been thinking extensively about over the past several years with respect to locomotion, those being effort or energetic cost and balance. So I've been fascinated with walking since I was a first-year graduate student. And like many of you, I learned in Kendall and Schwartz about spinal pattern generating circuits. And I was amazed by this possibility that such a complex behavior could be generated by circuits within the spinal cord. And like I believe some people have, I had a bit of a sort of naive view of the complexity associated with controlling locomotion. And that's something that I've really come to appreciate over the years, that locomotion is not just this cyclic pattern of flexion extension, but it's actually a really challenging task from an engineering or mechanics and control perspective. So what makes walking on 2 feet challenging? So in the robotics community, these issues have been really well established. And I'll just highlight some of those challenges here. So first, we walk with a really small base of support, particularly during single limb stance when one of our feet is off the ground. And so our center of mass is going to routinely exit this base of support, making us what we would refer to as statically unstable for most of the gait cycle. So in some sense, you can think about walking as repetitive falling and catching ourselves. We also have this intermittent contact with the ground. So we're cyclically forming and breaking contacts. And because of that, if we think about control, the mapping between, let's say, muscle force and segmental accelerations is not only nonlinear, which is not surprising, but we have discontinuities every time we have the impact with the ground. And so thinking about how you control a system where the dynamics are changing with these impacts is a really challenging control problem. And then when we think about degrees of freedom in the context of walking, we are what's called under-actuated. And the simplest way to think about this is that we don't have an actuator on our, let's say, torso that can directly command position and pitch. And so even if we can precisely control joint trajectories, that does not imply that we have precise control over body position or pitch. So coming up with effective control strategies is particularly challenging. So we can talk about this from a control perspective, but I think we all have an intuitive appreciation for how hard this problem is. And this year's quarantine has provided a nice case study for me as someone who studies locomotion, because I got to watch my son learn how to walk as we have been here together 24/7 for the last 7 months. So this is just a video of some of his first steps. And so there's dancing because we dance a lot at home. And he's walking toward his sister. And okay, great, he's walking. Now, the key point is that when he succeeds, it's really obvious that he recognizes this, right? As a 1-year-old, he recognizes how amazing this is. And as a viewer or a parent, if you've seen this before, we all celebrate, right? So we understand what it takes to go from just standing to walking. And the issue is that we fail a lot, right, when we're learning. And I think this has been, well, one of the best ways I've seen this point being made is from some of Karen Adolph's work, where she and her team study or observe infants both in lab-based settings as well as in real-world settings in their home. And what you can see is that this skill, this walking skill, takes months to develop. So if you think about step width as an indirect measure of how unstable you are, we see that over several months, infants learn or toddlers learn to walk in a sort of more stable fashion, but they also fail a lot. So, managing these instabilities is something that is, a skill that develops with lots of trial and error practice. So in the lab, we don't study infants, but we are interested in how different, let's say, states of neurological function impact locomotion. And as a mechanical engineer with interest in physiology, the way that we look at this problem is really by thinking about particularly mechanics and how those mechanics affect things like energy cost and balance or stability. Now, I'm also in the physical therapy department, and we do this study not only to understand sort of fundamental aspects of control, but ultimately we want to take this knowledge to influence therapy. So as most of you probably know, in my work, we have a large focus on this issue of asymmetry. And this is particularly relevant for people post-stroke. So this is just motion capture video from a participant in our lab. And one of the things that we would like to know is what, if we were to, let's say, design an intervention for this person, what should be the objective of that intervention? Is it rational to have an objective to make this person walk more symmetrically? So over several years now, we've been looking at different aspects of asymmetry, both in healthy individuals and people post-stroke. And I just wanted to share some of that recent work with you all today. So not surprising for most people here, one of the primary ways that we've been studying how people deal with asymmetries is to place them in what we might call an asymmetric environment, right? We place them on our treadmill and we make one belt move faster than the other. And so this is, we measure step lengths, we look at how asymmetry changes over time. And instead of talking about that process initially, I think there's a really good way to illustrate what makes this task so interesting from the perspective of mechanics. So the following is a video that I don't know if most of you have seen from Steve Collins's group and the others who are shown here at the bottom. And they developed a completely passive cart that can move against, you can think about this as sort of the flow of the treadmill, right? So, we all study split belt walking. This is someone walking on a treadmill. And we often think about using this in the context of rehab. So one of the interesting things is that if you build a cart that has wheels of different diameter, such that the larger wheel is on the faster belt, you see some really interesting sort of emergent behavior. So as we might expect, if you place the cart on the treadmill with both belts moving together, like a normal treadmill, unsurprisingly, the cart moves backward, right? It goes with the flow of the treadmill. But now, if I make one belt move faster than the other, completely counterintuitively for most of us, the cart will actually move against that flow. Right? And so the key insight here is that the cart is actually able to take advantage of work performed by the treadmill. So in other words, the treadmill, because of this difference in belt speeds, can actually transfer energy to the cart such that the cart moves in a reference frame that's centered in the lab. Now, we don't have wheels, we have legs, but we can also think about this issue, this asymmetry in sort of wheel diameters with respect to some of the asymmetries that we observe during adaptation. So when people initially walk on this treadmill, we know that they start with a limp. And so you can see this, this asymmetry that is driven in part by a challenge to balance and also uncertainty about this new environment. And over time, even though the belts are moving at this, in this case, a 3-to-1 speed ratio, we notice that the gait is much more symmetric. And I won't sort of belabor these results for too long because we've talked about this. But typically when we think about this task, sort of conventional wisdom is that people adapt to take steps that are approximately of equal length, and they do this in conjunction with minimum or a reduction in metabolic costs. But given what we've sort of illustrated here with the cart, one of our recent studies was aimed to really understand if people can use this treadmill to actually perform work for them. And so this is work that Natalia Sanchez presented here a couple of years back. So I'll highlight just the main points here to just talk through how this relates to our larger studies. So one of the methods that we use quite frequently in the lab, which you'll see through a few different iterations here today, is we provide people with visual feedback of their step length. So in real time, they see markers on their feet on a screen, and we can use that to guide them to adopt steps of different length. And if we change the length of the right step versus the left step, we can have these individuals walk with different levels of step length asymmetry. So the question is, how does this modification of asymmetry impact both the work that the treadmill is able to perform on the person and the amount of work that the person is performing primarily with their own muscles? So key results here are that as people take steps of longer length, so here that's denoted by the positive asymmetries, stepping further forward on the fast belt, we see that the treadmill performs more positive work on the person, right? So the person is essentially, you can think about them as sort of lengthening that step in a way that is maybe approximately similar to the larger wheel that you saw in the passive cart. And as the treadmill is performing more work on the person is performing less positive work, particularly with their legs. And we think this is important because positive work that's largely performed through concentric muscle contraction is energetically costly. And so we describe this process as taking advantage of the work performed by the treadmill. Now, not only do people sort of take advantage of this work in the domain of work performed by the legs, but the positive work that they're performing is highly correlated with metabolic cost. And so as they are reducing the work performed by the legs, we see this simultaneous reduction in metabolic costs. And if we look at the metabolic cost as a function of asymmetry, so again, we show that for positive asymmetries, people are able to take advantage of this work. And we see that there's this bias toward positive asymmetries being less energetically costly, right? So the prediction here then would be that if people are walking on the treadmill during adaptation and their objective is to minimize, I'm going to say something like metabolic cost, then we might expect that they take longer steps on the fast belt, right? So they might adopt an asymmetric gait. But if you've followed this literature for a while, that might sound counterintuitive, or you might say, well, this is unlikely to be true because this is not what we typically see during experiments. So this is just an illustration of some recent data that we've collected, a study that's under revision right now. But in a typical adaptation study, if we look at the step lengths on the slow and fast belt, we would often see that those step lengths approach each other toward the end of adaptation. But in a recent study, we tripled the amount of time that people were given. So we allowed them to adapt for 45 minutes. And we see that when given sufficient time, they do adopt this asymmetric pattern. And in addition, if we compare the sort of energetics of the pattern that they adopt after 15 versus 45 minutes. We see that there is a reduction in positive work over these last 30 minutes. And this reduction in positive work occurs with a simultaneous reduction in metabolic costs. Right? So this process of learning to acquire energy from the treadmill takes quite a long time. Okay? So this is 45 minutes of steady walking. So we've recently, been thinking about this adaptation process as being, essentially a form of, let's say, energy optimization, or maybe more generally, effort minimization. And the objective here then would be to, learn to use the work performed by the treadmill by walking with an asymmetric pattern. And there are asymmetries both in step lengths and step times. And this has also been explored by Jan Steenem and Julia Choi, particularly with respect to timing. And the key final insight of our work so far is that this process takes far longer than we might expect, or than we typically allot in our normal experiments. So so that's some of the work that we've done to really think about energy cost and asymmetry in the context of split belt walking. And so given that we've seen that in this condition, we might think of asymmetry as being the optimal solution, we have been asking similar questions for our post-stroke participants. And specifically, when you see someone walking with an asymmetric gait due to, in this case, damage to the brain, the question is whether maybe this asymmetry is also optimal in some sense. So one thing that I haven't mentioned is that when we look at these measures of step length asymmetry, our step lengths are due both to how far we place the leading foot in front of the body and how far our center of mass progresses over our trailing foot. Okay? So you have different strategies that you can use to modify step lengths. And so we recently, or a few years back actually, looked to see whether cross-sectionally in a sample of people post-stroke, whether there was any association with these asymmetries and metabolic costs. So when we looked at step length asymmetry specifically, we found a fairly weak association between step length asymmetry and metabolic costs. However, when we looked at foot placement asymmetry, now this is due to, again, the differences in where the leaning feet are placed, we saw a much stronger relationship between that asymmetry and metabolic costs. And so an obvious question then is, well, should we reduce asymmetry to lead to a more economical gait? And so we've been asking this question again by, one, determining whether people retain the capacity, people post-stroke, retain the capacity to reduce their asymmetry. We know that they do from work in, for instance, split belt adaptation. But here we're asking them to do this voluntarily. And with data, this is just one representative participant, but we can see that when people are given feedback to walk with steps of equal length, in the green case, in the sort of last trial here, they're able to reduce their natural asymmetry. However, when we look at the group level, so although most of our participants are able to reduce their asymmetry, as seen in the top left panel here, there's no systematic change in their metabolic costs. So in other words, they're able, even though they are walking with a more symmetric gait, we don't see at the group level that it's either more or less costly. And the similar result has also been observed in a couple of other recent studies, right? So we think this is a pretty consistent finding. However, I just mentioned that our step lengths can be composed of different contributions. And so if we look at that asymmetry in foot placement, so we refer to this as the step position contribution, we actually found that the change in this contribution was significantly associated with changes in metabolic rate. And specifically, people tend to have what we refer to as a negative asymmetry in this domain. And as they move toward more symmetric foot placement, we saw that there was those individuals tended to reduce metabolic costs, whereas people who tended to exaggerate that asymmetry in order to walk with steps of equal length would increase metabolic cost. So the strategy that people use to, this is people post-stroke, the strategy that they use to modify metabolic cost, or excuse me, to modify step length asymmetry, it matters, right? It influences whether or not that's going to be immediately beneficial in terms of their energy cost. So, you know, as I mentioned sort of at the onset here and in the title, we're not only concerned with energy costs, we are also concerned with this issue of balance, which is you know, one of those more challenging things to study in the world of biomechanics. And so a natural question is, you know, whether asymmetries and asymmetric walking patterns have a negative impact on balance, right? This is an intuition that we might naturally have. And so maybe this is one reason why you would like for people to walk more symmetrically. Now, there's several different ways that we could measure balance. I'm only going to talk about one of them today. And specifically, talk about some recent work that we've done looking at a measure called, referred to as whole body angular momentum. And so to measure this quantity, first we do whole body motion capture. So putting, sort of 80 markers on people. We then use simplified estimates of segmental kinematics and geometries. And momentum, we think about angular momentum, we measure it specifically about an axis that projects through the center of mass. And you can think about this as a measure that tells us something about the effort required to arrest a fall. In other words, if you are falling forward, the moment that you need to generate about the center of mass to arrest that fall will be dependent on the angular momentum that you have at that time of impact. So we know that this metric is typically kept to be relatively small during gait. And we think that reducing angular momentum could be one way to improve balance control. So when we think about balance, we often think about two aspects of balance. One being what we call proactive. You could think about this as when you encounter, let's say, an icy surface, you both slow down and you walk with shorter steps. In some certain cases, we may widen our step widths to increase our base of support. So we think about those as proactive, but we also need to respond to perturbations. And so for that, we think this is one of the more important aspects of balance control. And we study this through use of perturbations during walking. So what we do is we have people walk on our treadmill. And now instead of thinking about adaptation, where we have fixed differences in belt speeds, we apply discrete perturbations as people are walking. So during the swing phase of one of the legs, we will accelerate the treadmill. And what you can see on the bottom figure here is that the angular momentum becomes more negative. And positive values reflect essentially backward rotation, and negative values represent this sort of forward falling motion. And so we asked in a set of healthy participants whether modification of their asymmetry had any influence on their ability to recover from these perturbations. And the hypothesis being, or one hypothesis being, if asymmetry impairs reactive control of stability, then we would expect that they take longer to recover, for instance, or have they're more perturbed when they're walking asymmetrically. When we looked at one measure of angular momentum, which is the integral, we like to think about this integral as telling us something about how far, how much people are falling during a single step. So we can see that when we accelerate the treadmill, people fall forward, right? So we have this negative momentum. That forward falling is mostly arrested on the subsequent step cycle. And then a few steps later, they are essentially back to their normal gait. So there are multi-step recovery processes during this task. Now, what we actually found in this study was that these imposed asymmetries had no effect on the recovery of whole body momentum. So in other words, no matter whether people were walking with longer steps on the right or left, when we applied these perturbations, they had the exact same effect on the whole body momentum for both the perturbation, baseline, and recovery strides. So at least in our healthy participants, asymmetry did not seem to be associated with this measure of balance. So obviously we want to understand this relationship in the context of walking post-stroke. And to do that, we first have to recognize that when we look at measures of angular momentum during walking post-stroke, we see our peak negative value, so where people are essentially falling forward the fastest at this transition from the paretic to non-paretic step. So this is not all that surprising because they are, during the paretic step, they're standing on the more affected leg. Now, when we ask people to walk with a more symmetric gait, so in other words, reducing their step length asymmetry, so what we found is that this actually leads to an increase in that forward momentum right at this time around non-paretic foot strike. And so what we think, one reason then why people may choose to walk with this asymmetric gait, even though they retain the capacity to walk more symmetrically, is that reducing asymmetry could actually heighten instability. So in other words, as we move left on the figure to the right, we see this increase in momentum, and this might be perceived by the participants as being sort of less stable and more threatening. So to kind of conclude here, running out of time, a lot of our work, of course, is focusing on this issue of asymmetry and thinking really carefully about some particularly counterintuitive cases about the sort of cost or benefits of these gait asymmetries. When we think about split belt treadmills and how people learn to walk on them, we really think that this is a unique tool to study how people acquire assistance from the environment. And this made the processes or algorithms that we use to learn this task, we think may have parallels with how people learn to use devices like exos or exoskeletons. Right? The second major point here is that our intuitions about gait asymmetries can often be maybe wrong. And what we've been really trying to do is to test these intuitions and test alternative hypotheses. One of which is that, and it's maybe not surprising to some of you, but asymmetric patterns could actually be optimal in a certain sense for some stroke survivors. And this is more for our sort of clinic. When you think about the clinical application, we often hear about movement quality in the clinical literature, which is essentially a measure of a deviation from some norm. But using this as a way to guide therapy, I think it has some sort of conceptual problems, particularly if we try to correct deviations from some norm without resolving underlying impairments in things like muscle coordination. This could actually be more problematic for the patient, even though they maybe look more like someone who is less impaired. So I'll stop right there and thank you for your time and answer any questions that you may have.
All right, I thought that was fantastic. I have a quick question first, just to give some context to this result that you sort of had in the first half of your talk, where you showed that, I'm not sure if 10 or 15 minutes in to split belt adaptation, subjects were symmetric and almost perfectly symmetric. And then 45 minutes in, they became sort of systematically asymmetric a little bit. And then that seemed to correspond to a reduction in metabolic effort, right? So I'm just curious, like this reduction in metabolic effort that you saw, like, so how does that compare to if you put people on a regular tied belt treadmill for 45 minutes, Are both of the, is the effort in both cases higher than what it would be on a tide belt at both of those times?
Oh.
Is there a reduction from 15 minutes to 45 minutes on a tide belt, or is it pretty flat?
Okay, so there are a couple questions there. I'll address the first part, which is, so if you think about the cart that Steve and his group developed, that sort of points to the possibility that you could sort of walk for free, right, in some sense, right? The treadmill could perform all the work for you as it does for the cart. In which case you might expect that even if you're not able to do that perfectly, maybe you can walk with a lower cost than what you do when the belts are moving at, let's say, their average speed. So far, we have not observed that. We have not observed people walk more cheaply on the split belt treadmill, even after 45 minutes, than what they would do if the belts are moving at the same speed. But, and you know, I think there are some reasons for that. One of which is the cost to swing the legs. And that's something that we're sort of looking at through more of a sort of simulation perspective currently, but those results are fairly preliminary now. The second point was about extended walking on a treadmill in general. And typically when we think about steady state effort for a task of, let's say, constant speed, we measure metabolic cost. We like to give people about 6 minutes, and we, at least at that time, we see that the metabolic cost is relatively stable over those last 2 to 3 minutes. We have not looked at consistent walking at a fixed speed for 45 minutes, so I can't speak to what would happen over that time.
Okay, thanks. All right, so Amy Bastian has a question where she says, great talk. I tend to think of split belt adaptation as first learning predictable treadmill dynamics, some kind of cerebellum dependent adaptation. And then once learned, the gait pattern can be optimized to take advantage of that fast positive work from the belt. These seems consistent with the time course of what you show. Is that in agreement with your thoughts?
Yeah, so I think there are several things going on here at once. So in terms of, I think a lot of people are thinking about, let's say, error-based learning. We do know from, Alex Vasquez's work and others since then that as people walk on the treadmill, there is a change in how you perceive the belt speeds. And so you can think about this as a prior that the belt should be moving at the same speeds, and you receive an error essentially at the beginning of adaptation. And over time, you actually perceive that these belt speeds become closer together, right? More symmetric. So I think there's a sensory component to adaptation that is perhaps separate from what we're seeing in the motor domain. And I think that's a matter of debate. During early adaptation, one thing that I didn't mention here is that, and you can see in the video, is that people are highly perturbed, right? One of the first things that you think intuitively is, do not fall. And we've shown that, if you have people, let's say, hold on to a handrail, they are less perturbed during early adaptation. So I think that there's an initial instability that people are trying to manage during this adaptation. And that is due in part to the fact that they have a prediction about the world that is wrong or erroneous. So yes, so I do think that there is an early part of this adaptation process that is due in part to these errors in the prediction about the world. But I think interestingly, you can sort of explain that same process primarily using energetics. So we really need some novel way to sort of pit these against each other to really understand the relative contributions of errors and specifically effort in the context of adaptation.
Okay, so thanks for that. JJ asks, do you have any thoughts about how the brain might measure energy cost?
Yep. So this is, I sort of alluded to this earlier, but what I actually think is that, so energy cost is what we measure, right? We can measure metabolic cost, we can measure mechanical work, we can measure forces. And I don't necessarily think that the brain needs to measure, let's say, metabolic cost. I think, and there's lots of, a whole world of studies about effort-based, let's say, decision-making, where effort is really what I might refer to as a, sort of a psychological construct, right? It's due in part to forces generated by muscle, but it also due in part to other cognitive processes that may reflect the influence of things like reward. So what I really think is happening is that we are attempting to sort of minimize effort, and that effort is going to be correlated with things like metabolic cost and muscle force. Now, that's that's sort of difficult thing to establish because that effort is not a physical variable that we measure directly. So there are, of course, regions in the brain that represent effort. I think the anterior cingulate cortex is one, based on things like descending motor commands. And we also have feedback from the periphery about muscle force, accelerations, so from Lena's talk yesterday. And all these things together can give us a indication of effort being exerted throughout the gait cycle.
Okay. All right, well, thanks a lot. There are a few other questions, but I think in the interest of time, we need to move on. Maybe you can take a look at them in the Q&A and get back to people. But I think that was fantastic. Thanks, James.
All right, thank you.
Okay.
Let's see.
So our next speaker is, sorry, our next speaker is Shruti Sukumar, and she will be speaking about effort expenditure links control of vigor with decision making.
So can everyone hear me and see my screen?
Yes.
Awesome. Great. First of all, I'd like to thank the organizers for an excellent program so far. I've really been enjoying myself. And I'm excited to talk to you about my work, which is on how effort links control of vigor with decision making. So I'm going to start off with an example. Imagine you are picking apples in an orchard, and it's been a relatively good orchard so far. You've had a great run of apple trees and collected tons of apples. So one interesting question is, when you're at a tree collecting apples, when do you decide to leave that tree and move on to the next tree? Now, this kind of stay or switch decision has been studied quite extensively in ecology, computational psychology, and neuroscience. But let me pose another question to you. After you decide you want to move on from a tree, how fast do you actually move to that next tree? Now, consider an alternate scenario where your run of apple trees hasn't been quite as good. You've not collected as many apples, but you have to make the same movement to that final identical tree in this new orchard. How does the vigor of your movement to this last tree now change? So this is the central question of my presentation, which is, does the quality of the environment in which you're moving actually modulate your vigor? So we're going to turn to optimal foraging theory for some answers. And one question they widely considered in this field is, in an environment when reward is or food is distributed in clusters or patches, how do animals decide when they want to leave a patch of food in favor of another? Many of you might be aware of the seminal marginal value theorem that answers precisely this question. So Charnov states that an animal must leave a patch it is currently foraging in when the capture rate of that patch equals the global capture rate of the environment. Global capture rate quantity defines how good your environment is. So consider that first apple orchard where you're collecting tons of apples. That is an orchard which is higher quality, which has a higher global capture rate. Broadly, this global capture rate is defined as the net harvest in an environment or a habitat minus all the costs of moving to these different patches in that environment, divided by the total time spent in the environment. More concretely, it is defined by this equation, where in the numerator you have the sum over all the patches in the environment of the net harvest in each patch minus the cost of moving to each of these patches, divided by, once again, the sum over all the patches in the environment of the duration spent in each patch, plus the movement duration to each of these patches. So the classical MVT theorem by Charnov answers the question, when should we leave a patch? And to answer this question, he assumes that the time spent in a patch or harvest duration actually optimizes this global capture rate. So it's selected so that you can maximize your global capture rate. So let's actually see what happens in a patch when an animal enters that patch. So for this, we're going to focus on the net harvest in a patch, which is given by the function f of th, and see how that changes with respect to harvest duration in the patch. And it looks like this. So you can imagine when an animal enters a patch, initially, as they're harvesting reward or food, their harvest goes up. But as the animal continues to overstay in the patch and deplete the patch, this net harvest starts to decay. So when should you leave this patch? The theorem says that when the rate of harvest or capture in this patch equals the global capture rate of the environment, that is the point that determines how your optimal harvest duration, also given by the equation on the left below the global capture rate. So this has been empirically verified in foraging studies on birds and animals and ecology, and has also been extended to human behavior. But the theorem makes a very critical assumption, which is that travel duration between the patches is not selected like harvest duration to optimize J bar. Rather, when you select harvest duration based on what we saw, travel duration essentially comes predetermined in the environment. But what if travel duration is also selected to optimize your capture rate? This is the premise considered by Yoon and colleagues in their 2018 paper, in which they present a more generalized framework in which travel duration is also selected to optimize J bar, making the selected specific to each patch. So now it becomes TMs selected for each movement, and it also parameterizes the cost of moving between patches. So what does this theorem say about how fast we should be moving? So once again, consider the global capture rate function, and let us focus on what happens during movement. For this, we will visualize how the movement cost or expenditure changes with different durations of travel. And many of us know this is what it looks like, particularly as you move towards the left on the x-axis, as your movement duration decreases or vigor increases, we know that the expenditure relating to the movement will also increase. So how fast should you be moving? The theorem says, very similar to the classical MVT, that at the rate, when the rate of expenditure of the movement equals in magnitude the global capture rate of the environment, that is a point that defines the optimal movement duration between patches in the habitat. So the takeaway from this generalized framework is that global capture rate or quality not only determines how long you should stay in a patch, but also how fast you should be moving between patches. So going back to our research question, within this framework, the answer seems to be yes, the quality of your environment will modulate your vigor, but how does it do so? So let us consider our prescription for movement duration from this generalized framework in an environment represented by that orange slope with prescription TM star. What happens if you're making the same identical movement in another environment where the quality, where the global capture rate actually increases? Here, the prescription of the theorem, or the prediction of the theorem, is that in this better environment, the movement duration, optimal movement duration, actually decreases, which means you will be moving faster in the better environment. Further, over here, we are going to consider the effect of foraging effort on global capture rate. So now your better environment actually becomes your low effort environment, and your worse environment is your high effort environment. And the prediction is that in your low effort environment, your movement vigor is going to be higher, giving us our first hypothesis. Following from the classical MVT and everything we've seen so far, we get similar predictions for harvest behavior, where we know that in the better environment, your harvest duration is going to decrease. And in our case, where environment global capture rate is determined by effort, the prediction is that in the low effort environment, your harvest duration actually goes down. So together, our hypotheses talk about how global capture rate changes your movement vigor as well as your harvest duration. So to test this theory, we recruited subjects to come into our lab and perform arm reaching movements. They sat in front of a robot arm with a monitor at eye level, and they grasped the end of the robot arm, which was affixed with the grasp sensor to measure their grip force, and made arm reaching movements. As they moved, a cursor was controlled on the screen. We recruited 20 young adults to perform this experiment, but we discarded data from 2 subjects because they were unable to complete the experiment in a reasonable amount of time. On the screen in front of them, subjects saw the foraging task that they were supposed to perform. They controlled a cursor on the screen, which they should move to the patch in order to collect reward. Once in a patch, they could increase their grip force. They got visual feedback about their grip force increase until they reached a threshold. And when they were at the threshold, when they maintained their force at that threshold, they received a discrete reward at a decaying reward rate. At any point in time, they could decide to stop harvesting reward from the current patch and move on to the next patch. A running score counter at the top of the screen indicated to them how much total reward they had got over the course of the experiment. This was important because we gave them performance-based bonuses to keep them engaged in the task. So critically, we changed the effort with which they foraged, and we did this by adding mass to their reaches. Added mass was simulated through acceleration-dependent forces from the robot and was cued to the subject by changing the appearance of the cursor. So for a non-zero added mass, their cursor was blue in color and its size changed relative to the amount of added mass. So how much mass did they carry between in the experiment? So they performed these reach and harvest trials in 2 blocks, the low effort environment and the high effort environment. So in the low effort environment, they carried mostly 0 kg added mass, so no added mass. And the high effort environment, they had an added mass of 3.5 kgs. Critically, in both environments, they had a small subset of trials in which they carried intermediate added mass of 2 kgs, equivalent between the 2 environments, which we called the probe trials. So these reach and harvest, these environments were performed by the subjects in counterbalanced order. So we measured reach vigor through 2 metrics. One was the peak velocity of the reach, and the other was the travel duration. So we wanted to test the effect of global effort or environment effort on vigor. So we compared the metrics of vigor between the probe trials in the 2 environments. Remember, the probe trials are equivalent in the effort requirements. That is, they required only 2 kg of mass to be carried between the patches, but they differ based on the environment to which they belong. So we compared peak velocity as well as travel duration between these probe trials in the 2 environments. So let us see what subjects actually did. First, we look at how peak velocity normalized to the subject average changed with respect to trial number. The low effort environment was modulated as such. Compare that to how it was modulated in the high effort environment. And let us remember those intermediate trials are actually probe trials in which they carried a mass of 2 kgs. So what is apparent from this graph is that within each environment, when the immediate mass changed from, let's say in the low effort environment from 0 to 2 kgs, subjects actually changed their vigor in accordance with that. And they had similar behavior in the high effort environment as well. But critically, in those probe trials, when they had to carry 2 kg mass, their peak velocity seemed to be different between the 2 environments. To see if this really panned out, we plot peak velocity with respect to added mass, and we see those within environment effects, as we alluded to previously. But critically, the difference between the peak velocity in the probe trials between the 2 environments turns out to be significant. More specifically, their probe peak velocity is faster or higher in the low effort environment. This result was mirrored in their travel duration, where their travel duration with respect to the probe trials in the low effort environment was shorter. So subjects modulate their vigor in response to both immediate as well as a history or global environment effort. So going back to our hypothesis, we see from our empirical results that when we're considering a particular movement, based on the history of effort for the same movement, the movement vigor actually increases after a history of low effort. So let's now focus on what happens during harvest behavior. So first, when the subject enters a patch, they need to maintain their force above 30 newtons, at which point they get discrete rewards. In this case, we're calling that berries. And on the right-hand side, we have a visualization of what their grip force looks like and where they get berries corresponding to that grip force. So we wanted to see if the total number of berries they collected changed between environments. We saw that there was no significant difference between the number of berries collected between the environments in which effort changed. So we decided we wanted to see what else contributes to subjects staying longer in a patch. So when a subject enters a patch, they are it's enforced that they maintain their grip force below 10 newtons as they enter a patch so that they're not over gripping as they're moving between the patches. So upon patch entry, they need to go from that 10 Newton threshold to 30 Newtons. And we call this phase the grip ramp up phase. So we wanted to see if environment effort or global effort expenditure actually affected this grip ramp up phase. We quantified the grip ramp up behavior through two metrics. One was peak rate of force during ramp up, and the other was grip ramp up duration. Again, because we're looking at the history of effort, we're going to compare those metrics of harvest behavior between the probe trials in the two environments. So we found in terms of peak force rate, when we plot with respect to environment effort, that in the low effort environment, subjects had a higher peak force rate than that in the high effort environment. This was similar in grip ramp up duration as well, where subjects took less time to ramp up their grip force in the low effort environment as opposed to the high effort environment. So going back to our hypothesis, even though we did not find a difference in the number of berries collected, and I'm happy to discuss some reasons as to why that was the case in the question phase, we did find that durations with other aspects of harvest behavior, specifically grip ramp up, was modulated due to a history of effort. So together, our empirical evidence shows us that global effort expenditure does affect both movement vigor and harvest behavior. So going back to our apple example, the empirical data so far suggests that after a history of a really good run of apple trees, you're going to be moving faster than that second orchard where you didn't collect quite as many apples. When you're moving to that final tree, I want to emphasize that. So a couple of limitations which we hope to address in our future work is relating to global capture rate. One is how other ways of modulating global capture rate will have an effect on vigor. And the other one is how is J-bar actually updated in the environment. But I wanted to conclude by pointing out some of the contributions of this work. We present a paradigm in which global capture rate is modulated by changes in effort costs, particularly movement effort costs. We showed that reach vigor is modulated by changes in both immediate as well as global effort expenditure. And finally, we have presented and corroborated a unified framework that explains the changes in vigor as well as harvest duration by changing global effort expenditure. I'd like to thank my lab for providing their friendship, community support, especially during these times. I'd like to thank my advisor, Dr. Leah Ahmed, for the support, and our collaborator, Dr. Reza Shadmer, the MLMC committee for giving me this opportunity, specifically the reviewers, and our NIH funding. And I'd like to thank you all for listening to my talk, and I welcome your questions. Thank you.
Sorry, I'm unmuted now. Okay, thank you very much, Shruti. We have several questions for you. First from JJ, does the difference in velocity that you found for H1 reflect an after effect linked to the environment and not a difference in vigor? This seems to disappear in the last probe trials.
Yes, so there's two things I want to say in response to that. One, we do see that difference within each environment in response to the mass change. So it's not that subjects are just continuing to do the same thing as before when the mass changes between the environments. And secondly, yes, it appears to disappear. Sorry, it seems to disappear in that last probe block, but we didn't find that to be statistically significant. So we didn't find an effect of probe block number on the change in probe trials between the two environments. So based on that, we're taking this difference that we're seeing so far as some evidence to the fact that it's changing due to effort history.
Okay, Dieter Jiger asks, is vigor the same as speed, or are there additional measurable aspects of vigor?
Good question. So in this talk, yes, we are considering vigor to be the same as speed, but typically it's sometimes referred to as the inverse of the sum of reaction time and movement duration as well. But since we don't have a measure of reaction time over here, because when subjects want to move out of a patch or start moving is not cued by any target, we couldn't use that as a metric of vigor. So we took it just to be inversely proportional to travel duration, which in our case is velocity.
Alkis Haji Yosef asks, could a history of low effort allow for increased vigor in the probe trials due to less background fatigue?
Less background fatigue. So our experiment, I would say that our experiment wasn't too long. So we had just about 200 trials per environment. So I wouldn't make the claim that it was due to fatigue in the background. And additionally, we had a lot of checks where we counterbalanced the order in which these trials were performed or these environments were performed. So I think integrating over all of that, we don't really consider that these effects were based on fatigue. I think that's the answer I have right now for that question.
Okay. Josh Kashabak asks, says, when I think, sorry, things are jumping around the screen on me. When I think of this general framework, we have the push of vigor / dopamine and the pull of energy. Can you capture anything in between? Is this theory falsifiable?
Oh, that's a good question. I mean, obviously we need to test or make additional tests to see if this theory is falsifiable, but I have to think about that more to see, to be able to answer what those tests can be. So maybe I will get back to that question when I'm typing out answers.
One last question.
Sure.
From Rini Barghisi. The change with probe trials for peak velocity was much steeper than movement duration. Why might that be? How do you calculate movement duration?
Great question. Yeah. So definitely we saw that effect in peak velocity to be much, as you said, steeper than movement duration. It's because movement duration generally tends to be a noisy measure. And specifically for our case, because like I said, we don't have like a specific reaction time. We just take the duration of travel, that is the time spent in between patches, as being the movement duration. So this by definition tends to be more noisy, as it isn't computed through like rigorous thresholds of when the acceleration moves above a particular threshold and when the movement stops. We would just want to see what amount of time subjects spend outside the patches without collecting reward.
Right, but if it's, the question is about being sort of steeper, right? So there's an issue of sort of signal to noise ratio, but I mean, I guess I don't remember personally. Was it in fact a sort of like a steeper or more sensitive relationship to peak velocity than to duration? Because that wouldn't be explained by noise.
I think the relationship just was noisier. I'd have to look into this further to answer why. My first instinct is to answer that this is just because of the noise and because we are calculating the total amount of time spent outside. But I'll have to look into it more before answering why the slope itself is different.
All right, well, thank you very much. I really appreciate hearing your talk.
Thank you for all your questions.
All right, the next talk is by Yu Du from Johns Hopkins. And his talk is titled, When Going Can Be Faster Than Stopping, Rethinking Response Inhibition as a Flexible Decision About Whether or Not to Act.
Okay, can someone confirm you can hear me and see my slides? Yeah, okay. All right, hello everyone. Since it is around 12 o'clock in the Eastern time, so I'm gonna start my presentation with a piece of cake. I'm sorry, in case you're hungry. Okay, so imagine now there is actually a piece of cake in front of you at this moment. Okay, and it is so delicious and so colorful. What would you do to it? Some of you may already start to think that, well, am I eating it using my hand or using a spoon? You are making the decision about what action to make, right? Some of you may also think that, well, am I going to eat this cake right now or wait until after this conference so I can have some time to make a cup of delicious tea and enjoy it with this cake? It is the decision about when to initiate an action. What I am thinking right now is, am I going to eat this cake at all? Right? I may have the intention to eat it because I'm really starving right now, or I may have the intention to not eat it because I know it has too much sugar. Okay. So the decision between the intention to eat it or the intention to not eat it is the decision about whether to act or not to act. Much has been known about that what and when and whether decision are distinct processes in volitional control when we can internally generate those decisions, like the cake example given here. However, under most cases in motor control, we are required to produce speedy movements in responding to external stimuli, which involves some reactive control. Right. So for those cases, much attention has been given to owning the what decision and when decision. For example, we often hear the term action selection, response time, reaction time. Right. One particular example is that one study by Hayes and colleagues, it has been found that we are able to independently and voluntarily control the action about the decision about what action to make and the decision about when to initiate an action, even though we are required to quickly reactive to the stimulus. But in this presentation, I'm going to focus on the third type of the decision, which is whether to act or not to act, which has been relatively overlooked in the past in the motor control field. One popular paradigm to study the decision about whether to act or not to act is the stop signal test. People are required to respond to a go cue as quickly as you can, right? But occasionally a stop signal appears following the go cue, sometimes early, sometimes late. And in those trials, people are required to withhold the action that was intended to execute to the go cue. And we often are able to do so, even though the stop signal appears later than the go signal. And this universal phenomenon has been conceptually accounted by a horse race model, where we assume a go process and a stop process accumulate to hit a fixed threshold upon the appearance of the go cue and the stop cue, respectively. And whether we can successfully withhold the action depends on the race between these two processes. Right? If the stop process hits the threshold earlier, then we can successfully do so. As you can notice that in this race model, the stop process grows much faster than the go process, which leads to the prevailing thought that the stop process is a more privileged function than the go process. For example, this stop process has been termed like action inhibition, response inhibition, which is considered as a hallmark of executive control. Right? And a lot of effort has been made to try to figure out what's the neural mechanism or basis behind this dedicated stopping function, while less attention has been given to the go process here. So according to the race model, it seems that the whether decision is asymmetrical, which privileges stopping over going. Right? But the interesting question here is why stopping is more privileged than going. Right? If we look at the go process, we notice that in the stop signal task, people's response time are usually very sluggish, around between 400 milliseconds to 600 milliseconds, which is unusually long, right? So we suspect that actually the go process here does not only determine whether an action to be performed, but also determine when we initiate that action. So that being said, the go process conflates the decision about whether and the decision about when. Right? While the stop process seems only involves the decision about when to act or not to act. And we suspect that this may be the reason which causes the asymmetrical pattern between the stopping and going decision in this type of model. Okay. So it is our purpose to experimentally look at the decision about whether to act or not to act without confounding the decision about when to act. Okay. So in our simple experiment, we asked participants to view a circle which moves vertically downward to the horizontal line near the bottom of the screen. And what they need to do basically is just press a button or do nothing when the circle crosses the horizontal line. And this design just ensure that we limited the freedom to control when to initiate action and put the whether decision in isolation. Okay. And whether they press the button or do nothing depends on color of the circle. If the color is white at that particular moment, and the participant need to press the button at that moment when the circle crosses the line, okay. Or they do nothing when the circle is black. Okay. In half of the session in the experiment, the circle always starts from the white circle, which indicates the initial intention to press the button in this condition. Right. In 70% of the trials, the circle stay in white. That means participants need to press the button when the circle crosses the line. However, in the other 30% of trials, the circle changes its color to black on the fly, which requires participants to switch their initial intention to press the button to not press the button. Okay. So this session resembles the traditional stop signal task. And we are aimed to test the stopping decision here. And in order to test the go decision, we reverse the color of the circle. But in particular, the circle now always starts from the black color, which indicates that the initial intention to not press the button. And the participants need to keep that intention in 70% of the trials because the color doesn't change. While they have to switch their intention to not press the button in the other 30% trials when the color changed to white. In the whole experiment, we counterbalance the color in order to control some perceptual effect. And we also counterbalance the order between these two sessions, so in order to avoid some learning effects. Okay. From now, I'm gonna call this session, which we examine the stopping process as the responding to not responding condition, and I call the other session where we testing the go decision as the not responding to responding condition. Okay, so in order to test how quickly people can make the decision in both conditions, we manipulate the time at which the circle changes color in order to vary the time available to make the decision in each condition. So for example, in the responding to not responding condition, the decision time is between the color change and the target line, which is 500 millisecond point. I'm going to show you the data from one example of participants. Remember, this condition is from responding to not responding, which starts from the initial intention to press the button. So you can predict that when the decision time is very short, this participant always fail to switch the decision and always press the button when the circle crosses the line. Right? However, when the decision time is long enough, this participant always successfully switch the decision and withhold the button pressing movement. So to construct the speed accuracy trade-off across all for each individual, we calculate the percentage of accuracy at each decision time. And here I show you the average speed accuracy trade-off curve across all participants, which show you the similar pattern we saw in this individual participant. Okay, now in the other condition, which involves not responding to responding, we also manipulate the decision time. And it is defined between as the interval between the time color change and the time when the button was pressed. Okay. And similarly, we see the same behavioral pattern when the decision time is very short. this participant stay with the initial station and do not press the button when the circle crosses the line, while this participant successfully pressed the button and switch the decision, of course, when the decision time is long enough. And according to the race model, right, one would predict that the decision time needed to make the go decision in the not responding to responding condition would be slower than the time needed to make the stopping decision in the responding to not responding condition. However, we observe the opposite results. Okay? So now we confirmed by the area under these two curves, we show that actually the time needed to make the go decision in the not responding to responding condition is shorter than the time needed to make the stopping condition decision in the responding to not responding condition. So to further numerically estimate how fast they can make the decisions, we use a simple model to feed out data. So this is a particular trial start from the white circle, which has the initial intention to respond, and then later on the color changed to black. Okay. And the participant need to press the button or do nothing at the deadline constrained by the white line here. So we assume that in this type of trial, from the responding to not responding condition, initially you have the intention to press the button. But then you, upon the appearance of the stop signal, you make a decision to switch to not press the button at a random time. And then afterwards, you stay with this decision or intention to not press the button, okay, until the deadline posted by the external time constraint. And whether you press the button or do nothing at this time constraint is depending on which decision is available at that particular time. Okay, so in this case, if the decision available time is longer than the average time you needed to make the decision, then you can successfully withhold the action that was intended to execute. However, in some cases, when the available time is shorter than the time needed to make the decision, then you failed to withhold the action and still keep pressing the button at the post time constraint here. So it turns out our model, as you can see here, feed the data very well. And by comparing the average time estimated by our model, we found that, again, the average time need to make the go decision in the not responding to responding condition is generally 30 milliseconds faster than the time needed to make the stopping decision in the responding to not responding condition. Okay, again, the main conclusion is we found that going is faster than stopping in our experiment. Okay, so by far I demonstrate you the major and primary finding from our experiment, and the following two slides I'm going to quickly go through some additional analysis which confirmed our estimation from our model is reliable and not subject to some potential confounders. So first, we need to make sure participants settle the default intention to press the button or not press the button correctly in each condition. If they do so, the performance accuracy in those trials that color does not change would be very high because they have the initial intention. Meanwhile, the performance accuracy would be very low in those switch trials if the decision time is very short because they cannot successfully switch the initial intention to the other decision. Okay. It turns out our data confirm this prediction, except for one participant who looks like have some random guess or anticipation about what type of, whether the incoming trial has a switch color or not switch color. Okay. So the second confounder is very common in all of those stop signal tasks, which is we cannot observe the actual decision time people use in the responding to not responding condition because there's no overt response if they cancel their response, right? So remember, we define the decision time they use based on the timeline, which is at the 500 millisecond time point. So, which inherently assume that if there is a misfired response, okay, the response would be very accurately produced at this exact 500 millisecond time point. Okay, this is ideal, but not realistic because people sometimes can press the button earlier before the line, and sometimes they can strategically delay their response later than the line to buy additional decision time. And this bias in this actual decision time from the ideal decision time will overestimate or underestimate the average time they need to make the decision in this condition. So to make sure this is not the issue in our model estimation, we first check the response time distribution for each individual. And we assume if they statistically delay their response, right, you would see the skew distribution and delay the response time. But it turns out all those individual distribution, as shown by the black line here, are symmetrically centering at the 500 millisecond time point, which is confirmed by bootstrapped confidence interval of the magnitude and the skewness of the distribution. Well, you may think, well, people may not need to delay every trial at all, right? Sometimes they only need to delay the trial when they become more cautious. For example, if the preceding trial requires some action cancellation, they probably will try to delay the response time in the current trial by additional time to make this decision. We perform the same analysis to those particular type of trials, and we see the similar symmetrical pattern of the response time. And it confirmed that people do not statistically delay their response. Okay. However, even though the distribution looks pretty good, but it's still, you can see, if you see the mean reaction response time produced by each individual, some people have a slightly delay relative to the target line, and sometimes some people have the slightly earlier response compared to the 500 millisecond line. And overall, nobody is perfectly respond on the line, right? So this deviation from the actual response time and the 500 time point would also bias our estimation. To account for that, we approximate the true decision time for each individual by incorporating the response time extracted from their own distribution. And we found the resultant speed accuracy trade-off does not differ from the original analysis, either on the population level and on the individual level. Okay, so the previous two slides just confirm that we're pretty confident about our model confidence, and as well as our conclusion from the experimental finding. Okay, so to recap what we found in this simple experiment. Okay, first, what we found is we replicate the previous finding that we can rapidly make a stopping decision, like withhold the action that was intended to be withheld, withhold the action that intended to be made, right? Like a pedestrian who is about to cross the street must prevent himself from crossing the street because they're probably a faster right turning car approaching. In addition, we also found people are able to quickly make a go decision. Right? For example, a pedestrian who is standing on the curb upon a stop sign can quickly switch the decision to cross the street if she noticed that the bus she wants to catch is about to leave. Right? So most interestingly, we found that in our experiment, going is actually faster than stopping, okay, which is contrary to the traditional finding or prevailing interpretation from the race model. This is kind of surprising because we would predict that the decision time needed to make this bidirectional decision is symmetrical, but it turns out not. But the reason why going is actually faster than stopping is still a mystery and it remains to be answered. We have some preliminary guess, like at the normative level, we probably guess this asymmetrical pattern between the going and stopping is because of Pavlovian bias, because we're generally better at responding than not responding to get some positive rewards. But this is remains to be determined again. Okay. Secondly, the opposing results from in our study that going is faster than stopping to the results reported in previous stop signal tests that stopping is faster than going is probably determined by whether we control the freedom to determine the when decision. Right? We control the when decision here. They don't have the freedom to decide when to initiate action. But however, in previous stop signal tests, people can voluntarily control when they initiate the response, or perhaps they have voluntary volition to control when to stop a behavior, right? So if you allow them the freedom to control the when decision, then they can buy some leeway to favor in either of those decisions. So taken together, this opposing results, we suggested that the whether and the when decision may be supported by distinct processes. But however, whether they are augmented on top of each other or they are mechanistically independent is still an open question. Okay, and finally, even though we are focusing on the behavioral level, but we notice there's a lot of attention having paid to try to understand the neural basis of the privileged stopping function, which is very important. We don't deny that. But as we've shown here, the stopping decision is actually just one side of the coin of the decision about whether to act or not to act. So we suggested that it may be helpful to reconsider the neural basis with respect to more general decision framework about whether to act or not to act. In addition, similarly, we also noticed some study try to figure out the neural basis by feeding the race model to the neural signal. Right? But we suggest that when doing so, it is better to consider the when and whether decision as distinct processes rather than conflating them into one mechanism. Right? So I want to thank Alex Delaney and my advisor Adrian, who contribute a lot to this work, and as well as other members in the Black Lab who gave valuable comments to my presentation. And also thank you all for your attention.
All right, thank you very much. We have, it was a nice talk. We have a few questions. First, from JJ says, isn't the difference between go and stop the fact that it is not always possible to stop a movement while it is possible to execute a movement later? And maybe sort of just more general, I'll sort of add, so what do you think like the sort of the why is for why you might get this 30 millisecond advantage for quickly going versus stopping?
So first to answer JJ's question, I think it's a fair assumption, but it's also fair to assume that these because so in our experiment we constrain the time to respond, right? And it's kind of different from the like single reaction time task where you only determine when to press the button or make a response, right? You don't have to make a decision whether you go or not to go, which I think matches with JJ's question. It is not always to execute a movement later because we have a time constraint. You either no go or not go, or either no go or go, right? Press the button or not press the button. And you can get a reward if you don't press the button in certain conditions. So I think it's different between this time response paradigm and the simple response time that you can always execute a response later. And also answer your following question is, I mean, we don't know the reason. It's probably there's some physiological factor that you can activate your muscle faster than suppress the muscle activity, or you have some initial like a neural state in the neural state space. You have some strong resistance to suppress the action rather than initiate the action, or as we propose that at the normative level, maybe you have some Pavlovian bias, which I think all of those possibilities can be tested.
Okay. Giacomo Ariani asks, thanks for the nice talk. Did you also try a condition in which instead of switching to a no response, you switch to a response, e.g. a different finger or hand? Your model would predict that the go decision should have the same time course between the switch and the no switch in this case, right?
So I would say that I don't know the answer whether it will be faster to choose one action among two compared to the speed we made here. You only need to press the single button. You don't need to decide which action you make. And again, I think that possibility can also incorporate not only when and whether, but also including the possibility about the decision about what action to make. So I think it makes the make the additional decision that participants need to make. So perhaps they probably will be slower in that situation than what we observed here.
Okay. Rich Ivory asks, is movement, vigor, or speed the same for responses in the two conditions? if faster in the no to go, some failures would now be recorded as successes, assuming that the late pressed no to go are recorded as errors. Might this yield the observed advantage for go?
I'm sorry, I don't quite follow the question. So
I guess maybe the heart of it is how many failures do you have in these conditions? And
when we switch the color,
yeah, he's asking whether whether failures can maybe account for the difference. So if you don't, how many failures do you have? What fraction of trials are there failures?
no, I think if you're talking about the trial when the color switch, it depends on the decision time, right? And as we show here, that to very low decision time, the failure trial, the amount of failure trial is kind of similar, and when the decision time are very long, and then the accuracy is pretty similar across these two conditions. But if you're talking about the no switch trial, then it's also similar, as we shown by this slide. When the color doesn't switch, they have the kind of 100%, near the 100% perfect level, right, for the choice. So I may further think about this question, but I still don't quite follow like what this question is asking. I'm sorry.
Okay, maybe you guys can go back and forth offline.
Yeah.
Okay, thank you very much. Our final talk before a little 10-minute break is from Adam Smolder, and he's going to be, the title of his talk is Monkeys Exhibit a Paradoxical Decrement in Performance in High Stakes Scenarios, i.e. they choke under pressure.
Alrighty. Hi, everybody. Hopefully you can see my screen and somebody will interrupt me if you can't see or hear things. I'm Adam Smolder, and I'm going to be sharing with you some recent work of ours showing that monkeys exhibit a really interesting behavioral phenomenon that, to our knowledge, previously has only been demonstrated in humans. So here to demonstrate for us today, we have Scott Hoke, who's a professional golfer playing the sport for years, and he has to sink a 2-foot putt. Now, those of us here who have never even touched a golf club in our lives could probably sink this putt most of the time. But the key difference here is that this is for $200,000 to win the Masters. So what happens? For those of you who can't see the video, he didn't win the $200,000. He missed the putt. So why does that happen? This guy is professional. It's his job. He sunk this putt and so many harder hundreds of times before. And yet when it matters most, he fails. And Scott's not alone in this either. There's plenty of examples of this all over professional sports. You can find a lot of really fun top 10 lists. These are all examples of what's called choking under pressure. When the rewards are at their highest and you'd want to be doing your best, instead you do worse. Now, it's not just professional athletes who choke. Us everyday people choke all the time as well, even in laboratory settings. So for instance, here's an example of work where humans were performing a sensory motor task. And you can see that with increasing reward sizes, performance originally gets better, but then for the highest level of reward, worse. Not just sensory motor tasks either, cognitive tasks like puzzles and the like can also show choking or are chokeable. And it doesn't have to be money that's the incentive. Things like test anxiety, the presence of an audience, and more can all lead to choking. So what I'm getting at is that this is a very widespread phenomenon that crops up in many different ways. Overall, it's best characterized by this relationship between performance and reward. Whereas rewards go up, you initially do better, and then worse. So why is it that there is this inverted U relating performance and reward, that we don't just get better as rewards go up? Numerous psychological explanations have been put forward to explain choking, but regardless, the underlying neural mechanisms aren't well understood. There's been some beautiful non-invasive imaging work that's shown parts of the brain correlated with choking under pressure versus incentives and the like. But if we want to study this at the cellular level resolution, at the highest spatial and temporal resolution that we can, typically we would use an animal model of a behavior. The only issue in this case is that we don't know if animals choke under pressure. It's been demonstrated that animals can improve performance for higher rewards, but that other side of the inverted U hasn't been shown to our knowledge. And so here we sought to determine if animals, specifically monkeys, will choke under pressure. So we trained 3 monkeys on what we call our speed plus accuracy delayed center out reaching task. You can see how there's a little marker on the end of his finger that he uses to control a cursor on a screen. To start a trial, the animal had to bring the cursor into a central target. Then after a short period of time, a reach target would appear, beginning a variable length delay period. At the end of the delay period, the center target disappears. That's the go cue. The animal has a short amount of time to move the cursor over into the target, land in the target, hold there, and then receive reward. Now there's a few small differences that we have in our task from the normal delayed center out. The first is that you can see here that we cue the possible reward size for succeeding the trial at the same time as when we show the reach target. We do that by the color of the shape inside the target. You can see the 4 different reward sizes and how often they showed up that we used over here on the right. And what I want to highlight is that we have this small, medium, large, equally present, getting bigger and bigger reward sizes. But then there's this gigantic and rare jackpot reward. So what we're trying to see is, will the animals do better as reward sizes go from small to large, and will they choke for the jackpot? So that's the first thing. The second key difference is that we made the task difficult by limiting the amount of time the animals had to reach to the target, and by limiting or by shrinking the size of the reach target to roughly get to about 70% success rate when we were training with small through large rewards. So that's why we call it the speed plus accuracy task. The reaches have to be both fast and accurate. Now, the first thing that we want to look at is how success rate changes as a function of reward. So here I'm showing one animal, and what we see is that as reward size increases from small to large, performance gets better, success rates go up. And perhaps as the title of the talk has spoiled, indeed for the jackpot rewards, we see that monkey N does worse. And this is what we define here as choking under pressure. Quite literally, for a higher level of reward, the animal is performing worse. And it wasn't just monkey N that showed this. All 3 of the animals that we trained on this task showed this full inverted U relationship between performance and reward. And so from this, what we would say is that all 3 animals choked under pressure at our speed plus accuracy task. Before we move on, I want to note that this is pooled across sessions. If you look at individual sessions, the animals choke on nearly every one of them individually. And also, if you look at just the trials in the first half or the second half of a session, the animals choke in both halves as well. So from this, what we would say is that it appears it is reliable across and within sessions in our task that these monkeys are performing. Finally, for one animal, monkey F, we trained a second task that we dubbed the precision task. The reason being that there wasn't much of a time or speed requirement, so much as the challenge being the animal had to keep their cursor within a path that was presented at the same time as the reach target, where if they broke that path, that would be a failure. So even in this task that didn't really require speed, shown in black here, monkey F still choked. And even after doing the task for a month, if we look at just the last 8 sessions in olive here, you can see that he's still choking. Overall, we see that all 3 animals choked under pressure, so it's consistent across the animals. The phenomenon appears to be reliable across and within sessions, and for the one animal that we tested, robust across tasks as well. Now, it's important to consider that our jackpot reward was both rare and very high in magnitude. So could it be that either of these factors individually are what's causing the choking that we're seeing, or are both needed? We examined if rarity on its own could cause choking under pressure by running an additional series of experiments with one of the animals, monkey E, where we had a 5th rare large cue introduced. So this cue shows up as often as the jackpot reward, 5% of trials, but it's the same size as the large reward. So if rarity alone was driving the choking that we observed, we would expect the rare large performance to be at roughly the same level as the jackpot rewards. This is not what we see. So in black, you can see the animal is still choking under pressure like normal for the jackpot rewards, but for the rare large, there is a small, technically not statistically significant performance drop. Certainly not, though, to the level of the performance drop we see for the jackpot. So from this, we say that rarity alone doesn't seem to explain the performance drop that we observed. We then examined the opposite question, where if you had a common jackpot reward, would they choke for this? So specifically, it's showing up as much as the small, medium, and large, but it's the same size as the jackpot. And same idea, if the magnitude of the Q alone is what's driving choking, we would expect the common jackpot to have similar performance to the jackpot reward. And once again, this is not what we see. There's a, once again, small but not statistically significant performance drop. What we take from this overall is that in our task and experiment, it appears that both the rarity and the high magnitude of the jackpot reward were needed to cause the choking that we saw. Now, the next step is to ask what changes in behavior with reward are leading to the observed inverted U's that we saw in the success rates. It could be that the small and jackpot rewards have basically the same behaviors that are causing failures, or they could be failing in completely different ways. We looked at a lot of different behavioral metrics. What I'm going to do is first show you a couple of perhaps the more obvious ones, and they're confusing trends that don't exactly explain the choke, but I want to then highlight two key behavioral consistencies across all three animals that we think do well to explain the way that all of them failed for the jackpot rewards. So for these more obvious metrics, I'm referring to that you might initially jump to the notion of maybe they're just reacting and reaching slower for the small and jackpot trials. So if that was the case, we might expect that peak speeds for small and jackpot rewards would be lower, and that reaction times for small and jackpots would be higher. That's the case in one of the animals, monkey E, but we don't see that in the other two. Specifically for monkey N, it appears that he's actually reaching and for the most part reacting slower as rewards increase. And monkey F has roughly flat peak speeds across the rewards, but is reacting faster. So this on its own won't explain the inverted U's that we saw in at least two of the animals. We decided to take a bit of a different approach then to looking at behavioral changes. So follow with me here. This is an example speed profile for one reach. Consider that you can split a reach into two components. The first is a ballistic component where the hand is basically launching towards the target. And the second, a homing component, where you're trying to land exactly where you want to home in on that final endpoint. We wanted to examine how both of these changed as a function of reward. Specifically, is this ballistic launch covering more or less distance as rewards are changing? And is the animal taking longer or shorter amounts of time during that last homing leg of the reach? So for the first of these, to try and get a metric of how far that ballistic launch is covering distance-wise, we took the velocity profiles up to peak speed, mirrored them, and then integrated. The result, as you can see on this reach trajectory here, is that you get these ballistic endpoint predictions that tend to land short of where the actual reach ended and act as proxy to show where the reach would have landed if it was just the ballistic launch. So what we're curious to see is, how are these ballistic endpoint predictions changing with reward size? So here you would have like the reach target on the right, the center starting point would have been over here on the left. And showing one animal here, what we find is that as reward sizes increase, this ballistic reach endpoint prediction gets shorter and shorter on average of the target, of the reach target, excuse me. This held for all three animals. And so from this, what we would say is that it appears the ballistic portion of the reach is covering less and less distance as reward sizes increase. Now for the other side, to look at homing, we defined our homing time as the amount of time it took to cover the last third of the distance to the reach target. You could use the last half the distance or last quarter. The trends are the same as we found. we find that homing time increases as reward size increases. So with this last leg of the reach taking longer as they're homing in on the target, and the distance covered by this ballistic launch becoming shorter and shorter, we conclude that it appears the animals are approaching the target more cautiously as reward size increases. Now the question is, how does this monotonic change in caution translate to inverted U's in success rates? Consider that there are basically three ways a reach can go. The animal can go through the target, the animal can end up short of the target and then run out of time, or they can land in the target. For each reward size for each animal, we can break down all of the trials that fell into each of these different categories. For instance, for Monkey N's small trials, he has roughly 70% of the time landing in the target, about 10% of the time undershooting, coming up short, and about the remaining 20 overshooting, going past. So what we're curious about is, how do these failure modes and failure rates change as rewards change? There's a lot of data here, so I'm going to highlight the two things that are the same across all three animals. The first is that if you compare this light gray bar from large to jackpot, we see that there are more undershoots for the jackpot rewards in all three animals than there are for large. The second thing is, if you compare the dark gray or black bar from small to large, there are more overshoots for the small rewards. And this makes sense with what we were just talking about with caution. If the animals are becoming more cautious in approaching the target as rewards go up, they are perhaps being too careless, blowing through the target more often for small rewards, too cautious, coming up short more often for jackpot rewards, leaving these large rewards in the middle to be kind of a sweet spot with the least amount of failures overall. The result being the inverted U that we see in success rates. All right, to wrap things up, the biggest thing I want people to take away from this is that we saw that when we presented animals with higher and higher rewards, at some point they started doing worse. They choked for these jackpot rewards. This is the keyest, coolest thing that I want people to take from this. Specifically then, when we looked into what was driving the failures or the choking for the jackpot rewards between rarity and magnitude of the cues, it turns out that for our task, we needed both. And finally, when we took a deeper dive into what was causing the animals to fail, all of them choked due to this excess caution for jackpot rewards, leading them to come up short. I'd like to thank the senior authors of this work, Steve and Aaron, and also the other co-first authors of this, Nick and Patrick, who did the experimental side and a bit of analysis too into this. They are fantastic to work with and share equal credit for all of this. I'd also like to thank the other authors, Alan and Nicole, along with Aaron and Ozma for help with animal care and helpful discussions respectively. Finally, the Chase Lab, because they're wonderful, and funding sources below. And with that, I'm open to questions.
Okay, thanks, Adam. That was a nice talk. The first question is what's happening in the neuronal ensemble with choking versus successes? Are you measuring that?
No. So to be clear, this is all strictly behavior. And the reason why we're showing all of this first is because now that there is, from this standpoint, an animal model for choking, the next step is to start looking into the neuroscience of it. And there's many, many directions you can go from here.
Okay. John Krakauer asks, choking does not happen every time. Presumably you get better at high reward and can choke more often. Not exactly either or, as inverted U implies.
That's an interesting and fair point. I think the idea that you're going for is that there are aspects of performance that are presumably going to continually get better, but something else might be intersecting to like cause choking that's getting worse. This is an interesting point, and I suppose that you're right that the inverted U that we see tends to be more of this reflection of the output in success rates, which I guess we kind of point to with the whole monotonic increase in caution idea, right?
Right. So I mean, if that was true, the sort of the choking effect would be, some maybe bigger than it first appears, right? It would be, it's a difference between sort of extending that sort of positive slope and where you come down to.
Yeah.
If that were the case, who knows? Okay. The next question is from Alkas Haji Yosef. He asks, so is it that monkeys become more cautious when the potential reward is very high, but they suffer from a lack of practice with the cautious movement pattern, since the jackpot is rare? Do you get the same undershoots or slow homing time when the jackpot is relatively frequent?
That's a great question. We looked quickly into, like, for those common jackpot experiments that I talked about, the homing time and the ballistic reach endpoint predictions for those as well. They fell in between those of the large and jackpot rewards. So if you recall, I don't want to try and flip all the way back. Performance for the common jackpot was just a little bit worse than that for large rewards. And so it could be that, the way I view it is, at least, they are being more cautious, or the one animal we tested for the common jackpot is showing signs of being more cautious for the common jackpot than for the large, but it wasn't enough to see the or as far as it was for the normal jackpot to see the detriment that we did to success rates.
I see. Okay. We have time for one more question here. James Goodman asks, might this effect depend on the level of training? For instance, might a less thoroughly trained animal err on the side of speed rather than accuracy for the jackpot trials?
That is a awesome question that I don't, in our current data, have a great answer for. All of our monkeys were very well trained on center out reaching tasks even before they were trained on the different rewards, and then had weeks of, titrating the parameters to get to the levels that we wanted to before we even introduced the jackpot. So the question, I think, is, would a more naive monkey perhaps not show these same trends? And I would bet you the answer would be yes, because we see that lots of times novices who are just learning how to do something won't really choke at it. Typically, choking happens with at least some level of expertise, to what I've seen, and also if a task is sufficiently difficult. So without one of those factors, I wouldn't be surprised if you didn't see the same effect.
I just have one quick follow-up. So presumably, like when you have the common jackpots versus the rare jackpots, these are happening as, you have only a few monkeys, so right, or only a couple, and so you're doing this on different sessions. Is there like anything? Are there sort of any session to session effects? Like if on day 1 or day 25 there was a common jackpot versus a rare one on day 36. Is there anything to be learned from looking at the history?
Okay,
So,
if I'm reading your question right, you're asking is, do we see changes like across days in choking, basically, right?
Yeah.
So the answer to that is yes to some things and no to others. So one really cool thing that I didn't have the time to get into is that we ran earlier sessions with one of the monkeys, Monkey E, where we tried a different range of rewards than what we ended up sticking with for him. And he choked during the jackpot in a way that was kind of odd. He had more false starts. So he would jump the gun and start trying to reach the target more often. After we ran those sessions using the expanded reward range that we ended up sticking with for him for the sessions that we did here, he stopped choking in that way over the course of about a week of practicing with it. And so he got rid of, I guess, some of the bad and aberrant behavior, but evidently not all of it. And that's been human work too, where lots of times in laboratory tasks, people will adapt to, I guess, the presence of this giant reward being shown more often and will like stop choking. There's a cool paper from Taraz Lee and Scott Grafton from I think 2016, where they show in fMRI tasks that they're doing in the first half of the session, people choked more than in the second half as they adapted to it. So it depends, I think, on the severity and what all of the causes of choking are. It seems like that in some ways the animals would improve and get rid of some of these bad habits, one could say, that happen for the jackpots, but evidently not everything.
Okay. All right. Well, thank you very much. Really
Thanks.
appreciate it. Okay. So unfortunately, people, I've managed to let the time go sort of long for this first section to try to counteract that. And we'll try to come back at 1 p.m. so we can be a little bit closer to staying on track for the whole thing. I apologize for that personally. Thank you. So we'll reconvene at 1 p.m. 1 p.m. Eastern. Okay, I'm going to introduce our first speaker for this for this next block of talks, for the final block of talks this afternoon. And his name is Navendu Patil, and his name of his talk is Human-Inspired Task Level Regulation Helps the Simplest Dynamic Walker Avoid Falls.
Okay, can you hear me? And can you see my
Yes.
screen? Okay. Okay, so my name is Navendu Patil, and I'm a postdoc at Penn State, and this is a joint work with John Dingwall and Joe Cusumano. First of all, I would like to thank the organizers for organizing this meeting, and I'm glad that I'm able to attend it because of these times. So today I'm going to talk about how simple models, when coupled with experimentally informed observations of human data sets, could lead to surprising predictions about why humans walk the way they walk. So we know from James Finley's talk that walking is a really hard task, and it requires, which we have learned over a significant period of time. It is especially hard for older adults because they fall very frequently, and even though very few times they suffer injuries, the injuries are quite very serious, such as hip fractures and head injuries. And in general, we would like to quantify their fall risk so that we can come up with some interventions to reduce fall incidents. But the fall risk itself depends on number of biomechanical, neurological, and cognitive factors. And in fact, the best predictor of fall risk is how many times you have fallen off previously, which is not really a great sign, which tells me at least that we have a lot to understand as far as quantifying fall risk is concerned. But generally speaking, a catastrophic event such as fall is preceded by postures of the body which are not normally seen in normal gait. And so it is a large disturbance problem. And so we believe that fall avoidance is related to our ability to handle large external disturbances, which is basically the global stability. However, it is very hard to measure in practice. We can design perturbation experiments in labs, but to do it so reliably in a quantitative fashion would be extremely hard. So we resort to models here, and we basically use tools from dynamical system theory, which is nothing but a study of stability. So if we ask people to walk on treadmill, all they need to do is basically stay on it without falling off its ends. And we can do so in this task, in seemingly simple task, in infinite number of ways in principle. However, so there is not only a redundancy at the level of joints and muscles, but there is a redundancy in terms of strategies one can choose to walk on treadmill. And so we believe that the central problem that how the nervous system manages these redundancies to achieve the walking task is really an important question. And we believe that the understanding fluctuation dynamics of how people regulate task level observables, which we can measure in laboratories, could shed some light on how the nervous system achieves this control. So if you look at here, a previous set of experiments which appeared in Joe's and John's papers from 2010 and 2015, the subjects walked at 5 different speeds around their preferred walking speed as shown on the x-axis. And we look at simple task level observables such as speed. We look at the stride time series of speed as step speed, stride speed, and of the absolute position of the walker on the treadmill belt. And if you look at the speed, then we see a random looking time series around some average value, which of course is the same as the treadmill belt speed. But if we look at the position, then we see a drift for several tens of strides, either in the front half of the back half of the treadmill. So what it suggests is humans appear to regulate, control speed more tightly, and while they don't really so much appear to care about the position. And this can be quantified using measures which basically capture the autocorrelation of these noisy time series data. So what we have here on the y-axis is the DFA exponent, which is 0.5 if the time series is of white noise, and it is 1.5 theoretically if the time series is of random walk. So in the context of control, if a task level variable was optimally targeted, then what you would see as its output in experiments is a filtered output through, so to speak, through a mechanical system of the motor noise. Okay, so the time series that we would see in such case would still be largely uncorrelated, so that its a DFA exponent alpha would be close to 0.5. And if an observable was not corrected at all, then we would see its DFA exponent of alpha 1.5. And if you look at the step length and step time, although they are controlled to some extent, they are not as tightly controlled as, say, an optimally controlled gate variable. But if you look at the speed, then the alpha of step speed, stride speed series is close to 0.5. In fact, it is slightly less than 0.5, which suggests that the it is overcorrected, meaning every negative fluctuation in speed is followed by a positive fluctuation on average. But if you look at the corresponding measure for the position time series, then we see that it is closer to 1.5, in the range of 1.3 to 1.5, which means that position is definitely not tightly regulated as speed, which is consistent with what we also see in the data. So the question is, I mean, these are just two viable strategies on treadmill walking. Like in principle, we can walk on the treadmill if we maintain a position, say in the middle of the treadmill, but we choose not to do so voluntarily. Or in principle, we could have chosen some other strategy. So the question is, why are people trying to regulate speed, not just on average, which they would anyways have to do to stay on treadmill, but from one stride to the next? So this is really an interesting question, and we wonder if this has any implications, if the stability has any implications in answering this question. And so, especially the walker's ability to avoid to reject large disturbances, which would have implications on their fall risk. So we study this question using simple models, which have a rich history in locomotion. So templates, which are basically nothing but the simple models of complicated bodies undergoing locomotion. And these templates capture the task level behavior of such bodies, and using simplest model consisting of fewest possible parameters as possible and variables as possible. So these have been really useful in, for example, when coupled with optimal control framework, they yield useful predictions about the average trajectories of how for various motor control tasks, from reaching to walking, and especially using like suitable cost functions such as energy minimization. So, but these are primarily mechanical in nature. They are basically simplified models of more elaborated models with a high number of degrees of freedom, which are still able to capture the behavior at, say, so to speak, at the end effector level. So the similar model one can think of about how people regulate task level observables from one step to the next. Okay, so this has been basically the focus over the last decade or so in our lab, and it is inspired from this previous work by Todorov and Jordan within the optimal control framework, where they basically minimized. They said that one can obtain feedback control inputs through a cost minimization, where the cost is primarily driven by the performance error at the task. So Joe and John extended this basic framework to walking, where to account for the fact that when people walk, they also tend to have preferred walking speed and things like step length, preferred gaits. So they modified this original framework to make predictions about human walking data. And so here, the first equation is basically a state update equation. And let me just point out that X is here. It's a state, but in what we can measure in laboratory is basically variables like step length, step time, and position, say in the sagittal plane. Or if we are studying, say, lateral stability, then it could be width, step width, and body position, lateral body position. So these models are at the level of stepping variables, okay? Contrary to, say, more elaborate models of mechanical models of walking. And so what these models do, similar to templates, is they try to capture in the simplest possible way how people regulate fluctuations from one walking step to the next. And these models have been shown to be consistent with human data in the sense that, for example, we saw that people regulate speed tightly on treadmill. And if you construct a model which regulates speed, which as it is supposed to do, it also predicts that it predicts the correct behavior of position regulation as observed in humans. Okay, but if we construct a similar model, but which regulates position at each step, as expected, it does have a DFA of position time series close to 0.5, but it does not predict fluctuation dynamics of speed observable as observed in human data. So what this basically shows is that these motor regulation templates can be derived from human data sets, and they form basically simplest ways in which we can capture step-to-step dynamics. And so in this work, we are going to merge these two kinds of templates, the mechanical ones and the motor regulation ones. And so to study this problem of global stability. So the mechanical template I use is basically well known from the Kuo's paper. It's a simplest walking model which walks by itself on level ground with the help of this push-off impulse, which is applied just before the swing foot has a heel strike. So it has a completely unactuated stance phase. It has no continuous time control, or only the push-off is the free is the input one can choose. So when push-off is fixed at each step, it corresponds to open loop dynamics. And when we are going to impose different motor regulation strategies inspired from experiments to adjust push-off at each step. So we place this walker on the treadmill. The state of the walker in the frame attached to the treadmill bed could be described using two variables. One is the theta, which is a stance leg angle, and its rate of change, theta dot. And the push-off is applied. So what I'm showing here is the kth step of this walker. At each walking step begins after the heel strike, indicated by positive superscripts. So, and it ends again after the next heel strike, indicated again with subscript K plus 1. So at the heel strike, you see subscripts negative. And so if you want to prescribe additionally where this walker is on the treadmill in the lab frame, then we also need to specify its absolute position. So the step-to-step dynamics of this walker could be described using this hybrid Poincare map. It is a hybrid dynamics because it is a combination of continuous time dynamics and impulsive double support phase. And so we have this Poincare map F on a two-dimensional state space with P as the control input. So this map admits what are known as period 1 gates, which basically gates which appear, which repeat after every step. These are the fixed points of this map at a certain speed, which here is the same speed as the treadmill speed. So we look at these gates in the state space. So I have here a two-dimensional picture of the state space, theta on the x-axis and theta dot on the y-axis. And so the state space is divided into 3 regions. At a given stance angle, if the walker is, if the stance leg is moving too slowly, then it cannot swing past its vertical. So this is not where it cannot, this is in this region it cannot walk. Similarly, at a given stance leg angle, if the leg is moving too quickly, then it cannot have a heel strike and the walker falls forward. So there is just for a given stance leg angle, there is a range of angular velocities where the walker can have at least 1 step. And we call this 1-step region. And to visualize this region better, we scale the y-axis, the theta dot variable, to a new variable, such that these upper omega low envelope gets mapped entirely to the horizontal line 0 in the new coordinate, and this lower envelope gets mapped to the value -1 in the new coordinate. And so these are the 2 families of gates which are also observed in other passive dynamic models, the blue one being what is known as long period gate, and the red one being a short period gate because it has a lower period compared to the long period gate. So long period gates are known to be open loop stable, which means if you apply the same impulse at every step for a range of impulse parameters, you can achieve stable periodic gate, period 1 gate. So we are going to focus on, this is one representative long period gate that I've shown with a black asterisk. So we impose the motor regulation strategies inspired from human treadmill walking experiments on this walker. The first one is the speed regulation. At each step of the walker, we simply choose speed. We choose impulse such that we minimize this quadratic cost in the speed. So VK plus 1 is nothing but a predicted speed based on the walker's model if we were to apply impulse P in the previous heel strike. And V star is the target speed, which here is the same as the belt speed. So all it does, all this regulation strategy does is minimize this quadratic cost at every step. So it is not a priori clear if this is a good idea at all from a control design perspective or from a point of view of stability. So we would like to see if for arbitrary initial condition, if the walker trajectory approaches some steady state gate. And generally speaking, control engineers won't design such controllers. Although the speed does capture some information about the state of the walker, it doesn't capture obviously the entire information. Similarly, we can separately impose absolute position regulation on this walker, where we minimize now quadratic cost in position, where dk plus 1 with a superscript minus is the absolute position of the walker on the treadmill at next heel strike, when we have applied an impulse P at the previous heel strike. And so D star is the target position, which we, without loss of generality, set to 0, which is the middle of the treadmill. And again, we don't know whether this is a good strategy from stability point of view. And so we would like to see if a walker can handle arbitrary disturbances.
So Navendra, you're running out of time, so you need to start wrapping up.
Oh, okay. So let me skip to the local disturbance. So here I'm showing a sample disturbance plot where all 3 walkers are able to handle disturbance well, but the regulated walker is able to do reject the disturbances much faster. And this can be confirmed using flow key multipliers. And we see that both regulated walkers have similar local stability, and they are able to do better than the open loop walker. If you look at the global stability in the state space, every point here is the arbitrary, could be considered as arbitrary disturbance. And the yellow region here corresponds to open loop walker. So the open loop walker can only handle these disturbances such that those trajectories approach the steady state. If you look at the position walker, then you get a blue region, and with speed regulated, you get a green region. So you can see that the speed regulation is able to is able to increase global stability significantly. It is in fact 10 times the area of this basin of attraction is 10 times the area of the open loop walker. And we see the same effect if we look at the across parameters where the speed regulation and even the position regulation walker does better than the open loop walker significantly. And to conclude, I would like to finally say that we show that task level regulation has this big effect on walkers' ability to handle external disturbances, despite it not being not specifically designed to do so. Speed regulation enlarges and regularizes walkers' basin much more than unregulated walker. And this shows, and since this result is consistent with experiments, we demonstrate a functional connection between motor regulation and global stability. And also our results show that local stability may not reliably predict fall risk. And also our work highlights the question whether people choose regulation strategies from the perspective of minimizing fall risk. Okay, thank you. I'll take questions.
All right, thank you very much for that interesting talk. We are open for questions. So I'll start with a question. So if you're on a treadmill, doesn't it seem to make sense that you should start with, so what's the difference between position and velocity? If you want to control your position, the best way to do that is through velocity because it's a step ahead, correct? Given the fact that you're on that treadmill.
So if you are on a treadmill, you do need to maintain, you need to walk at the same average speed as the treadmill speed, but you don't have to do it by doing it at every step. So you could, for example, walk at different, you could take a step at different speeds correctly by choosing different speeds so that you are able to stay on the treadmill. So
you're controlling average speed, right? Or you
I'm controlling speed at every step.
Right, but ultimately that determines average speed, which determines your position. So
if you control speed, then it does not determine position because the previous position is not known while controlling speed. We don't use the information of previous position when we control speed. That's what speed regulation means. It only uses information from previous speed, not the position.
I'm not sure that I follow entirely, but let me move on to Maurice has a question also related to regulating speed versus position. So drifts in speed wouldn't be allowed in the task because consistent deviations from the desired speed across trials would mean you'd be walking off the treadmill.
Right.
So isn't just the fact that you're on the treadmill essentially requiring that you control speed?
Right. So, but a drift for several tens of steps may not be allowed, but maybe for a few steps it could be allowed. So it is possible, I think, to choose combinations of step length and step time so that you don't very tightly control speed at each step, but you are still able to stay on the treadmill. Mm-hmm. But I do agree that like drift for several strides would be difficult to handle.
Okay, so we have a question from Josh Kashabak. So are there model assumptions that the stability basins are sensitive to other than position versus velocity control? For example, the rate that a model can generate force or impulse or something else?
I mean, it could be. It's it's difficult to answer these questions. Like definitely, like we have much more control authority compared to what this model can do. So, like for example, impulsive control is not very good at like reacting very fast. So we think that we react in a continuous time. So there are other control authorities which we have at our disposal when we walk, which this model doesn't have. So those, but I don't really think that this could, like the basic conclusion here is that this motor regulation could have big effect on stability. And I think it would likely hold even for more like lab model at other models with other assumptions.
All right. And well, one last question from me. So just because you've gone unstable doesn't necessarily mean you're going to fall and injure yourself, right? You still have that mechanism to throw a leg out or throw an arm out and recover. So does that, so does your model, would that ability just add to your model in some way, or could it completely kind of negate, go in the opposite direction of your results, right? Because it's not the full story, right?
I mean, we don't assume how within step processes are controlled. So they could be, well, we can of course react in continuous time. So there could be, we can use those control authorities. So I don't think it would negate what we have. In fact, it gives us more inputs, control inputs to handle those kinds of disturbances.
Okay. All right. Well, I think it's definitely time to move on to the next talk. So thank you very much.
Thank you.
So our next talk is from Caroline. Caroline, would you like to share your slides?
Yeah, can you see this?
Yes.
Yes.
Great. One second, I'll just move this over here. Okay, brilliant. Well, thank you so much for the opportunity to share my work. I think this is a great meeting, so thanks so much to the organizers. So I'm Caroline Nettergrofen. I'm a researcher in Oxford, and I'm interested in the role of GABA in adaptation. So I did my PhD with Charlie Stagg and Ned Jenkinson in Oxford, and today I'll be presenting part of my PhD work in which I link M1 GABA to retention of an adapted state. So as you all know, motor adaptation is fundamental to navigating our world because our environment and our bodies constantly change. And so to keep up performance, we are required to adapt to this change. So for example, since you've all had to recently work from home, you might have had to get used to using a different computer mouse. So this mouse might have a lag, and you will make movement errors in the beginning, like on the graph in red, but you will quickly adjust your movements to those new properties of your mouse, and your performance will return to former levels. And then after delay, once we return to your department mouse, you'll make movement errors again, this time in the opposite direction, because you retain some of that compensatory movement. So just to get terminology out of the way, in my talk, I will be referring to the phase where people change their movements in response to a perturbation as the acquisition of an adapted state. And then I'll be referring to the phase where the perturbation is removed after some time, and people display an after effect that gradually reduces as the retention of the adapted state. Now, one framework of adaptation suggests that the acquisition on a visual-motor adaptation task primarily involves the cerebellum, but that the retention of this adapted movement relies on M1. And this is in contrast to other forms of motor learning, such as motor sequence learning, which is thought to involve M1 at the acquisition stage. So in motor sequence learning, GABA concentration measured from the left M1 hand area has been shown to correlate with the acquisition of a motor sequence. So we therefore hypothesize that in adaptation, where M1 is involved in retaining the adapted state, early M1 GABA concentration would correlate with the extent of that retention. And secondly, it's been shown that functional connectivity between left M1 and right cerebellum changes after performing an adaptation task. So specifically, the activity in left M1 becomes less synchronized with the activity in the right cerebellum. So you can see the post-adaptation phase here and the pre-adaptation phase here. So we therefore also wanted to test whether retention would correlate with the change in connectivity between left M1 and the right cerebellum. To test this, we had 15 healthy right-handed participants attend 2 MRI sessions where they were scanned either during a rotation task or during a control task. And I will show you the rotation session first. So inside the scanner, participants controlled a cursor on the screen using this joystick with their right hand. And they were instructed to hit 1 of 8 targets, so one of which you can see here in green. And this would be the optimal movement, and this would be the slightly imperfect participants movement. So after these baseline trials, we would impose a 10-degree rotation on the feedback. So again, this is the optimal movement, this is the participants movement, and this is the visually rotated feedback. And we increase this rotation by 10 degrees every 40 trials. So this rotation by the end of the experiment went up to 120 degrees. And then outside of the scanner, after some delay, we took the rotation away to assess retention. During task performance to assess M1 GABA, we collected magnetic resonance spectroscopy data from a voxel positioned over the left M1 hand area. And we also collected resting state fMRI data before and after task performance. Now, I mentioned that this was a within subject study, and participant attended another session, so the control session. And the only difference between the rotation session and the control session was that in the control session, we did not impose any kind of rotation. So people just shot targets throughout the session unperturbed. And the order of the session, was counterbalanced. Now I'm showing you here the MRS blocks acquired from the left M1 hand area. So each MRS block consisted of 53 individual spectra, which were averaged to increase SNR. And the MRS block acquired during the baseline trials served as a measure of baseline GABA. Then on the right here, you can see the voxel placement for the rotation and the control conditions. And the color bars represent the number of participants who have a voxel covered in the spot. And you can see that the MRS voxel placement was quite consistent. So there was no difference in voxel placement between the sessions, and coverage of the M1 hand area did not differ. Then below here, you can see an example spectrum from one of the MRS blocks of one of the participants. So in order to quantify GABA, we fit a linear combination of the spectral contributions of all of the different metabolites that we expected to be there in that voxel to the spectrum. So you can see the fit right here. And from this fitting procedure, we then obtain our GABA measurement. We then exclude all those GABA measurements that did not meet our quality assessment criteria, but for the baseline measure, all of the measurements survived. Then I'm showing you here the behavior from inside and outside the scanner. So you can see the control condition in blue, and then you can see the rotation condition in red. So you can see that they're fluctuating at around 0. And then as soon as we impose the rotation, they make this error, which then gradually decreases within the blocks. And we confirmed that there was actually indeed error reduction using paired t-tests, comparing the error at the start and the end of each rotation block. And you can also see that participants not only adapted, but they also showed this after effect that reduced then during the washout. So to actually quantify adaptation and retention, we calculated the average angular error during the rotation blocks from the rotation condition. And for the retention measure, we averaged the angular error in this during this early washout block, this first washout block in the rotation condition. Now, before testing our specific hypothesis on M1 GABA, we first wanted to see whether we could replicate changes in functional connectivity in the cerebellum that have been shown before. So this was because our adaptation paradigm is quite unusual in this use of a stepwise increasing rotation, whereas other adaptation paradigms mostly just impose one rotation. So we wanted to really see whether we're driving changes in the cerebellum that would be expected. So we set out to replicate this paper by Albert and colleagues, where they showed that after adaptation, but not after control, there's this the increase in functional connectivity of a cerebellar network. And in our experiment, that's also what we find. So you can see the cerebellar network overlaid as this magenta mask here. And then in red and orange, you can see voxels that show increased functional connectivity after adaptation compared to after control. To also test the specificity of this result, we ran the same analysis on a control network, so the default mode network, where we didn't expect there to be any changes due to adaptation, and there also were no changes in this network. We then extended this analysis from the Albert paper to see whether, if we look inside the rotation condition, whether the change in the strength of that cerebellar network from pre to post correlates with adaptation error. So that's indeed what we see. So you can see that those participants that increase the cerebellar network in strength, those are also the same participants that adapt quite well. So you can see zero adaptation error would be those participants that perform quite well on the adaptation task. And we see that there's no similar relationship for the strength change of the default mode network. And these relationships were significantly different. So next, we also wanted to test whether our results hold when we quantify adaptation using a model-based approach to be sure that this is not just because of the way that we quantified adaptation. So we used a simple single state state-space model to model adaptation performance. So you can see the red arrow curves overlaid over the adaptation data. And we found that our measures of adaptation, whether you quantify them in a model-free way, so the adaptation error, and our model-based adaptation parameter, they correlate highly, which is of course expected. And we also see that the relationship of adaptation with the change in strength of the cerebellar network doesn't depend on the way you quantify adaptation. So also adaptation parameters correlate with this change in the strength of the cerebellar network. So next, we actually then tested whether early M1 GABA concentration relates to the retention of the adapted state. So we find that retention, but not adaptation, correlates with M1 GABA, such that if you have high M1 GABA concentration at baseline, you retain more of the adapted movement. And these correlations, again, are significant, so it is really specific to retention and not to adaptation. We also tested whether this relationship is specific to GABA by looking at whether glutamate correlates with retention or adaptation, but found no relationship. So this is also quite specific to GABA. We then looked at whether the change in M1 cerebellar connectivity correlates with retention. And we find that those participants who decrease, who show more of a decrease in connectivity between left M1 and right cerebellum, those are also the participants that retain more of the adapted state. And again, there's no relationship with adaptation. This relationship is also specific anatomically. So we looked at whether maybe left M1 and left cerebellum, the change in connectivity correlates with retention, but that's not the case. So this is actually, as expected for a right-handed task, specific to right cerebellar, left M1 connectivity. And then lastly, we also had a look at whether M1 GABA correlates with the change in M1 cerebellar connectivity. And we find, again, a relationship. So we find that participants who have higher concentration of GABA at baseline, those are also the participants that show more of a decrease in connectivity between left M1 and right cerebellum. And again, this is specific to GABA rather than glutamate, which doesn't show any kind of relationship. So because we found this threefold relationship between M1 GABA, connectivity change, and retention, we then set out to further explore this result by using a mediation analysis. So what we wanted to test is whether the connectivity change between left M1 and right cerebellum might mediate the relationship between M1 GABA and retention. So a mediation analysis tests whether the observed direct relationship between two variables, so in this case M1 GABA and retention, might be mediated through an indirect pathway via a mediator. So in this case, M1 cerebellar connectivity change. And that's exactly what our mediation analysis shows from our data. So we find that regarding the question of what is the role of M1 GABA in retention, that this is the model that emerges. So high M1 GABA concentration before adapting relates to a decrease in M1 cerebellar connectivity, which in turn relates to increased subsequent retention. So to summarize, I showed you that adaptation increases connectivity in a cerebellar network in a performance-relevant way with the paradigm that we used. We find that there's a relationship between early M1 GABA and retention, and that this relationship is mediated by connectivity change between left M1 and right cerebellum. And we find that these relationships are highly specific. So they're specific for GABA, specific for left M1 and right cerebellar connectivity, and specific for retention in the rotation condition. So with this, I would like to thank my supervisors for their support, my lab group for all their help, and of course, thank you to everyone who is listening. And I welcome your questions now.
All right, thank you, Caroline, for that great talk. And we have a number of questions, so we'll get started. So Alkis has a question. He's asking, I noticed this as well. If you go back to the slide where you show the data for the learning, it seems that the control group shows after effects as well, but in the opposite direction. And why would that be the case?
Yeah, that's a really good question, and it was a mystery to me until I looked into the practice data. So I'll just show this really quick. I think you can see this now. So here you can see the practice, the familiarization period that we did in the beginning. And we had participants practice just for 32 trials outside of the scanner and inside the scanner. What you can see here is that as soon as we put people inside the scanner, you've got this little movement bias that goes away quite quickly, but you do have this, this offset, and that's quite consistent. So what I think was happening was what was driving this offset in the control condition was that because of the positioning inside the scanner, so we had people have the joystick on their lap, there's some way in which certain movements just get biased in a particular way. And this is something that both the control condition and the rotation condition experience. So I just flipped this and put it on here so that we can actually see whether this would explain that. And I think that would be my hunch, that the control condition just had this, is showing something from the initial bias.
So could that be affecting your measure of retention if you're in the adapted group?
That's a good question. So our measures of retention are independent of the control condition. So we quantified retention just as the angular error during this initial washout. And we also looked at, so when I was referring to the control analysis, I also looked at whether, for example, M1 GABA correlates with this offset in the control condition, and there's no relationship. So it seems to be something that is actually driven by this consistent adaptation process rather than some kind of unspecific change in just movement execution like the control condition shows.
Okay, let's move on to the next question. So this is from Ronan Mooney. They're asking, did you look at GABA and glutamate in cerebellum and whether there was similar or different modulation as observed in M1?
So this is not in this study. So this study, because you can't, other than fMRI, you can't collect MRS data from M1 and the cerebellum simultaneously, which would be great, but we can't do that. But we did a follow-up experiment to then look at cerebellar GABA, and that's what we see. We see that during adaptation, there's a change in right compared to left cerebellar GABA, and how much it changes in the right cerebellum, so specifically in the right cerebellar nuclei, correlates with the extent of adaptation. So I didn't have time to present this data here, but yeah, in a future meeting, maybe.
Okay, then we have a question from Valeria. She's asking, was retention measured short-term or long-term? And she's asking this because they have seen that the functional network that relates to short-term memory appears to differ from that, from the one that supports long-term memory.
Yeah, so the delay between the measurements was short. So it was at around 20 minutes. So it wasn't retention assessed days after anything. This was all done on the same day.
Would you expect to see similar results if you had waited longer?
I'm not quite sure. I think the kind of changes because these kinds of studies, they were also, so the delay between the two sessions was about a week. I also looked at whether there was any kind of trace of the memory after a week, and we didn't see any kind of savings or trace of this kind of adapted state. So I don't think, I wouldn't necessarily expect this to transfer over longer periods of time, but yeah, this would probably be something we'd have to test.
All right, I think
Well, I just had one quick question. So you're training this sort of, stepwise, this really by the end a really large 120-degree rotation. I think most people would probably think that it's likely that once you get to rotations that are anywhere in that ballpark, that a lot of the learning would be strategic or explicit. And so, do you have any thoughts on to what extent the results that you're showing might come from implicit learning versus strategization in the task?
That's a really good question, and I've thought about this. Unfortunately, I can't test this with this kind of data, so we were kind of wary of messing with the adaptation process any kind of way, because we wanted to avoid any kind of jerking movements inside the scanner to really make sure our GABA measurements are nice and clean. So we weren't really able to probe implicit or explicit adaptation. But what I can at least say from verbal reports, so interviewing the participants, is that people were hardly aware of any kind of rotation that we impose, which actually surprised me quite a lot until I looked at the individual subject level variance. So there's a lot of variance associated with a target that averages out across participants. And just the joystick is really hard to control. So even though there is this quite clear pattern at the group level, I think we succeeded in a way of driving adaptation that relies more on implicit processes, but obviously I can't be sure because we didn't probe this.
Okay. And the other association, of course, is that between sort of error and amount of learning here. So you're probing sort of the amount of learning, but you don't know whether the signal comes from how much the learning there was versus how large the error signals might have been.
I should mention though that during the workshop they do see, so there is visual feedback. So I would imagine if everything they did was just explicit, they would reduce the error a bit more quickly than we see.
Okay.
All right. Okay. So I think it's time to move on to the next speaker. You do have some questions that you could follow up on, Caroline, in the Q&A box. And thank you very much. Our next speaker is Ihsan from Reza Shadmir's lab. Good afternoon there. So he's going.
Hello. Cordelia.
You want to get started?
Sure. Let me put this. Great. Okay, thank you very much, Elia. And I want to first thank the organizers, Elia, Adrian, and Maurice, and also the reviewers for putting up a very much good work in putting all of this together. Before I start, I want to also thank and acknowledge the contribution of my colleagues, Paul Hage and JP, and of course, thank my amazing mentor, Reza Shadmir. So the work that I'm going to present today would be from the latest results from this new branch, the electrophysiological branch of our lab that works with marmoset monkeys, these very cute and good looking small monkeys that is really being a joy working with them. So hopefully you will also get interested. For those of you who are interested in working with marmoset monkeys, then this will maybe encourage you more to work with these animals. Okay, so probably I don't need to convince the audience of the MLMC that cerebellum is important, and cerebellum is important for building the internal models and predict the consequence of our motor commands. But what has been a major difficulty in the field was to get sense of how does the cerebellum actually do that? How does the cerebellum build these internal models and encode the learning or correct for the movements? Through two very excellent papers by David Hirschfeld from our lab right now at Steve Lisberger's lab. David and Reza has proposed this new framework that maybe not just single Purkinje cells are important, but the population of Purkinje cells are important, and that's what we look at. And so in that work, when they put Purkinje cells of population together, and they did that based on their preference for the error, what they saw is that these Purkinje cells, this computational unit, contributing to learning from the error that they actually have a preference for. So in the work that I'm going to present today, first of all, we are going to move from this macaque data set to marmoset animal and present that marmoset monkeys are actually very promising non-human primate models for studying motor learning and motor control, and also build upon on that framework and push it even further to infer more about how does the cerebellum encode the internal models. Before I dive into the science-wise and more on the kind of technical wise or methodological wise, we published a paper last year in Journal of Neurophysiology about how we train marmoset monkeys to perform saccadic eye movement tasks, and how we perform the surgery, designing the head post, and more importantly, how we build up a coordinate system to target deep brain areas, and specifically in our case, cerebellar vermis that we are recording from. So feel free to check that paper, and if you have any further questions, I will be glad to also address that. More recently, we also kind of write from ground up a software package named PSort to sort the simple spike and complex spike of Purkinje cells. For those of you who have worked with Purkinje cells, you know that what a hassle is to sort complex spikes. We are still in the beta mode and we have not released the software. If you're interested in helping us by providing us feedback, please feel free to shoot me or Reza an email, and we will send you the source code. Once we release this, it will be an open source free of charge for the community. Okay, great. With that out of line, and let's dive into the science-wise. So we are working with marmoset monkeys and they're doing saccadic eye movement tasks. So the task design is a very classical visually guided saccade task. And the task starts with the center fixation point. The monkey has to fixate at the center point for about 200 milliseconds. Then we jump the target to a new location. So the fixation point will disappear and a primary target will appear. The monkey's task is to make a saccade toward the primary target. So monkey make a saccade. When we detect the onset of the saccade, what we do is that we will jump the target to a new location. So this target will disappear, a new target will appear on the screen. And as a result of this, when the eye landed at the target, and the target is no longer there, and so when I land at this location, the target is actually a new location. And this is what has classically been suggested as a sensory prediction error, because the brain predicts that when it lands at the location, it should receive the target, or the target should be there, but it's in a new location, so it's against the prediction of the brain. So it's a sensory prediction error. And as a result of this sensory prediction error, the monkey make another saccade, what we call a corrective saccade or a corrective movement. And the monkey's task is to fixate at this point, and once it fixates for 200 milliseconds, it will receive the reward. If we do the same paradigm over and over again, there's no surprise that we are going to have learning. But in our task that I'm going to present the data today, it's a completely random task, and the net learning is 0. So each time that the monkey fixates, the target can jump into 4 or 8 random directions. And when from that primary target, also 4 or 8 random other directions. And so we are spanning the whole space, if you will. Okay, great. While the monkey is doing this saccadic task, what we are doing is that we are recording from a saccade modulated Purkinje cell. And most of the cells that we recorded from are located in lobule 7A of the cerebellum vermis. And we are confirming that we're actually recording from Purkinje cells by detecting simple spike and complex spike from the same cell. So that's important. And after recording a Purkinje cell and also recording a saccade-driven Purkinje cell, we are sorting the data. And so what's this simple spike and complex spike? It might be, for those of you that might not be familiar with the Purkinje cells. So the Purkinje are very unique cells. They are the sole output of the cerebellar cortex, and the output goes to the cerebral nucleus. These Purkinje cells have the usual firing simple spikes that they fire around 60 hertz, and but they, in addition to the simple spike, they also from time to time fire a complex spike. And complex spikes are, if you see here, is 50 milliseconds, is 5 seconds. So there are 2 orders of magnitude have lower firing rate. So they are firing at around 1 hertz. So they're rare events, and also the spike shape is very weird. Complex. And so we detect this complex spike, and how we confirm that they are actually from the same cell is by looking at the cross correlation between the simple spike and complex spike, and confirming that when a complex spike is happening, we had a prolonged suppression on the simple spike. Great. So we had simple spike and complex spikes from the same Purkinje cell, and also we want to now look at the learning and encoding and motor control and motor learning and answer these type of questions. Okay, what has been the difficulty in the field and what we want to do to address those difficulties? So it has been very well established in the field that if you detect align your data with respect to saccade onset, what we will see is that these simple spikes do in fact show a modulation to the saccade. So when we align to the saccade onset, we can see cells are pausing, bursting. So this is the same cell in different directions, bursting and pausing. What has been challenging is that when you look at the kind of tuning wise activities. So this cell is bursting in some direction before the saccade, pausing in some direction before the saccade, pausing, bursting, doing all kind of crazy things. And it's not consistent what it's doing. And this has been the difficulty in the field, that they can confirm that these are saccade-driven cells, but they cannot make sense of the tuning of the cell, what this cell is actually tuning for, other than just saying that this is saccade related. So what we want to propose here, and what's the framework, they not have just simple spike, they also have complex spikes. They're rare event, but they are there, and they're actually very important for the learning. So let's look at complex spikes. If I add, I don't know if you can see it, but if I add complex spike here, what you can see is that this cell has higher firing rate of complex spike, or probability of firing a complex spike in the rightward saccades, and less probability in the leftward saccades. So if I plot the probability of firing a complex spike based on direction, you can see this directional tuning for the complex spikes. And we want to use this framework. So we want to say that forget about the absolute coordinate system, right, left, up, down. Let's reconfigure our coordinate system based on which direction has the highest probability of complex spikes. Let's call it CS on, and we make that the origin of our coordinate system. And from there, we want to now establish a new coordinate system. So from there, the direction opposite to the CS on will be CS 180. And in the next slide, it will become clear why I'm defining a new coordinate system. Okay. Now let's look at the simple spike activity. So I showed you that we cannot make sense of simple spike activity all the way. So what's the case if we use this new framework? How can we get sense of that? So if we just look at, if I just collapse all directions together, what you will see that this is the velocity trace for a marmoset saccade, that the peak velocity is around 500 degrees per second, and the saccade duration is about 30 to 40 milliseconds. If I look at the simple spike activity during this saccade, we can see that over all directions, we actually see a modulation in simple spike activity. So overall, over all the cells, over all 110 cells that we recorded from, the simple spike activity bursts before the saccade and pauses during the duration of the saccade. But what this framework lacks is that now if I wanted to dissect this data set more into different amplitudes, there is no amplitude tuning. And if I also dissect it over directions, you get the same tuning get the same type of activity over all directions. So if I just use the absolute framework of right, left, up, down, I will not be able to disambiguate the amplitude tuning or the direction tuning. And this has been the difficulty. So what we are proposing here is that instead of using the absolute coordinate system, let's use the new coordinate system based on the CS on direction. And if we do that, what we will see is that in direction CS 180, we see the maximum activity, and in direction CS on, we see the minimum activity. And this is true for both high amplitude saccades, in our case, primary saccades here, and also low amplitude saccades, in our case, corrective saccades that have lower amplitude. So if we use our framework, we can actually get out the directional tuning. So we can see that for different directions in this new framework, the cell actually do produce different kind of activity. If you look here, you can see that the cell that in CS180, and the cell shows actually similar firing rate for high amplitude and low amplitude, and in CS on is different. So now what we pushed more based on our last framework is that saying that, okay, these CS on and CS off cells, or CS off is CS 180, are actually, they're not isolated from each other. So when there is an saccade in direction CS on, it's in direction CS on for some cells, and it's in direction CS off for some other cells. And these two population of cells are actually active at the same time. So we should not look at them in isolation, but you should look at them together. And based on this framework, and what we're doing is, we're going to subtract CS on activity from the CS 180 activity. And when we do that, what we'll see is that for higher amplitude saccades, we see higher activity in the population, and for lower amplitude saccades, we see lower activity in the population. So just take home message, if we just look at, forget about this new framework and look at just the absolute framework, we will not be able to decipher the amplitude or the directional coding. Using this new framework, this new coordinate system based on CS on, we will be able to decipher direction, and also we will be able to decipher amplitude of the ongoing saccade. Good. Now let's kind of switch gears a little bit, and now let's focus more on the complex spikes. So I will go a little bit faster. So complex spikes, as I defined, we put all the direction with the highest probability of complex spike in CS on. And so this was the only thing that we control for. But as you can see in direction CS off, automatically we will get lower amplitude and lower probability of complex spike. If you look at the activity through time, we'll see that after the encoding of sensory prediction error, this is the end of primary saccade, we see an increase in the firing rate in direction CS on, and we see a decrease in firing rate in direction CS on. And this is what drives these two. Okay, this was based on just the sensory prediction error. We want to add more to that. Is sensory prediction error the only thing that can drive complex spike, or can we also infer the primary saccade as also a sensory event? So to answer that, we looked at Q onset because monkeys fixating, and then all of a sudden we present a Q in an unexpected, in a random direction. If you look at actually the Q onset, so this is time from primary stimulus, what we see is that actually for primary saccades or the Q onset, we also see an increase in the complex spike activity. So it's not just solely for sensory prediction or event, but also for this Q event, we also see an increase in the complex spike activity. Now we want to push this further, saying that, okay, you saw this here, you saw this here. Maybe complex spike activity is not a sensory event, it's just a motor event. And if you look at actually, I realign the data based on just primary saccade onset, you will see an increase before primary saccade onset, and you also increase before corrective saccade onset. And you might naively infer that maybe complex spike is also both a sensory event and a motor event. But to answer that, there's a co-founder here, and this is the same area of time. So to dissect this more, we looked at the task irrelevant saccade. So the monkey is doing the task, but from time to time, when the monkey wants to harvest the reward, monkey makes some saccades that are not related to the task, but just saccades from different locations of the screen. The monkey just see a very blank screen in front of them. Once we look at those saccades, what we see is that there is no modulation of complex spike activity. So what we infer here is that, first of all, we see an increase in the complex spike activity for sensory prediction error. But it's not just for sensory prediction error, but for the other sensory events, we also see an increase in the complex spike activity. But comparing the sensory event with the motor events, our results suggest that it's not motor events, and the complex spike activity has an encoding solely for sensory events. So that's the take-home message here. Overall, if I want to just conclude, marmoset monkeys are very promising new animal models to start both motor learning and motor control. My talk today was more on the motor control side. We're going to expand this work and go to motor learning side as well. Our results demonstrate that population coding in the cerebellum may be via a collection of P cells that share the same preference for error. This was a replication confirming the previously published results. What we added here is that when P cells that share the same CS tuning are organized into population, their combined SS response predicts direction and amplitude of saccades. And also something that's new is that results showed that there was a modulation in CS firing rate around the task relevant saccades, while there was no modulation around the task irrelevant saccade. And with that, I would be happy to take your questions.
Oh, thank you very much for that fabulous talk, Maurice. So Maurice is he's asking, is the CS tuning used based on the time during the saccade or a much wider time window as implied in the talk?
Yep. So let me go back here. And so what I plot here as the CS tuning is, oopsie. Sorry. That means that I was on time. So what I applied as CS tuning here is the probability here is from 0 to 200 milliseconds after Q onset. So it's when the sensory event is happening. happening. But if I excite, I'll also get the same tuning, just because the reaction of primary saccades are about 200 milliseconds, so they span the same area of time. But to answer your question, I looked at 200 millisecond after the Q onset.
Sorry, you said Q onset a couple of times, but then you pointed to saccade onset. Which one is it?
So sorry. So let me make it clear. So we had the monkey fixating here, and the Q appears on the screen. Q onset. This is one part of complex spike. The other part of time is when at the end of primary saccade offset. So when the saccade land at this location and the target is in new location, we consider the primary saccade offset as the Q onset for the secondary saccade, because that's the point of time that the monkey can see that the target is in a new location. So this is the first sensory event. This is the second sensory event. And during both these sensory events, we see an increase in complex spike activity after that sensory event. Is that clear?
Okay. Yes. So maybe I just didn't understand, but when you talked several times about the relationship between recordings and sensory prediction error, but do you do anything to distinguish sensory prediction error from any other kind of error, like motor performance error or any other measure of error?
No, the only thing that so
motor performance error and the evidence would be the same, right?
Yeah, no, that's correct. That's why I'm saying that even I'm kind of going away from the notion of sensory prediction error. What I'm proposing here is that you don't, if classically you say that this is sensory prediction error, what you see at the end of primary saccade that drives the complex spike, what I'm proposing here is that even any sensory event can drive complex spikes. So I'm kind of going broader, saying that complex spike is not encoding just sensory prediction error. They are encoding visual events that are maybe surprising. So any prediction error or sensory prediction error, but it's still a little broader.
You don't show any demonstrated prediction though, right?
Sorry, say it again.
You're saying any prediction error, but there's nothing here to demonstrate prediction per se.
So the prediction here is that, for example, for this pawn, and when the monkey is fixating, and the prediction is that the target should stay at the same location. And when the target jumps, because also the timing is random, when the target jumps, that's against the prediction because you predicted the target to stay at the same location. So it's jumping into a new direction. And also from another line of work from Javier Medina's lab, we also see, and also Joshua Mattis, is that the complex spike also encode reward and also the CSUS, those type of events as well.
Okay.
So could the fact that you're seeing this CS on in response to the primary stimulus, it could still be a prediction error in the sense that they're expecting to see a stimulus in a certain direction, but then you provide it in in another direction? Is that correct? Like if you had a history of the stimulus always being provided upwards, and then you do a number of trials, and then that's followed by a trial where it's to the right, that would they're building an expectation for where they're going to see that primary stimulus.
Yeah. So to answer that question, I don't have the polished data to show you right now, but the monkey makes another type of saccade. So the trial ends here, but for the next trial to begin, the monkey should come back to the center of the screen and make another saccade. Okay. So I looked at those saccades back to the center of the screen. Those saccades are predictable because monkey knows that they should come back to the center of the screen. The direction is random because they are maybe in this direction, but they know that they have to come back to the center of the screen. But the paradigm of doing it is that this target will disappear and new target will appear. So it's a visually driven because I'm disappearing this target, appearing this target, but it's a predicted thing. Even for those saccades, I saw an increase in the activity of complex spikes. That's why I'm saying that this is mostly visually driven events. And maybe even if you had a good prediction about what's going on, still you will get complex spikes. But this has to be task relevant, because not any motor event, this piece here, saying that just if you look at all non-task relevant saccades, you will not see a modulation in complex spike activity.
Thanks for that clear answer. And so building on that, we're going to, Rich Ivory's asking, the lack of modulation for task irrelevant saccades is very interesting, especially since reward harvesting is most important part of the task for the animal. So is there presentation of any stimulus to mark the harvesting period?
So short answer is I don't know, because we have the data that when the monkey is licking and harvesting the reward, we had the data. We had to go back and kind of tag the data to get the time tags. So and look at the specific time that the monkey is licking. Do we have an increase in the complex spike activity or not? Colleague of mine, Paul, is looking at specifically at that question, and maybe in a short time he will be able to directly answer that question. But these are saccade-driven Purkinje cells, so I will not be surprised if they don't show any kind of modulation for reward, just because they are encoding saccade events or visual events that are related to saccades, not events that are relevant to food or tongue or other stuff. Hopefully that was clear enough.
All right, that was great. That's all the time we have for questions, but you do have a question from Andrew Jackson in the Q&A. So,
okay.
And it's time now for us to move on to our last plenary of the meeting.